Have you ever looked up at the moon and felt a sense of profound and quiet stillness? It hangs in the darkness of space, a silent companion on our journey through the cosmos. We have walked upon its sunlit plains and gazed upon its tranquil seas from afar. But what if there are places on the moon that have never seen the sun? Places of absolute cold and darkness, older than any story we have ever told. Tonight, we will wander through this question together, exploring a place of silent wonder. But first, allow yourself to settle in. Let the weight of your body grow heavy, sinking gently into the surface beneath you. Notice the quiet rhythm of your breath, a soft, steady anchor in the stillness of this moment. Before our journey begins, I wonder where you are listening from this evening. If you feel moved to, you might share your city and the time in the comments below, joining a quiet community of fellow travelers. For now, simply rest and let the day fall away. Our story begins not in the distant void, but with a simple, familiar sight. We begin with the moon as we have always known it, a gentle lantern in the velvet darkness of our sky. It is a presence that has calmed poets and dreamers for all of human history, a constant in a world of change. Before we travel to its most mysterious and hidden corners, we will first rest our gaze upon its familiar, peaceful face, remembering the quiet journeys we have already made. There is a unique comfort in the light of the moon. It is not the demanding, energetic light of the sun that calls the world to action, but rather a soft, reflective glow that invites quiet contemplation. On a clear night, it washes the world in shades of silver and grey, softening the sharp edges of the day and transforming the familiar into something serene and new. This lunar light has been a constant throughout the entirety of human existence, a silent witness to the turning of ages. It has guided nighttime travelers, marked the passing of seasons for ancient farmers, and inspired countless stories, songs, and works of art. It is a shared heritage, a celestial campfire around which all of humanity has gathered at one time or another, looking up to ponder its place in the universe. This gentle glow feels both immensely distant and deeply personal. It is a world away, 250,000 miles of empty space separating us, and yet it feels like a feature of our own world, a part of our home's nocturnal landscape. When we look at it, we do not feel the vast emptiness that separates us. Instead, we often feel a sense of connection, a quiet reassurance. The moon's phases, from the slender crescent to the full luminous orb, are a celestial clock, a rhythm that is both cosmic and deeply familiar. It is this familiarity that we will begin with tonight, this sense of the moon as a known and peaceful neighbor. Before we venture into the unknown, we must first appreciate the known. We must remember the feeling of standing under its gentle light, feeling the cool night air, and sensing that we are part of something vast and beautiful. This moon, the one that shines through our window, is our starting point. It is the anchor of our story, the calm harbor from which our journey of the imagination will depart. We will hold this feeling of serene familiarity with us as we travel, a quiet reminder that even the most mysterious places in our solar system are part of the same cosmic home. From that universal feeling of watching the moon, our thoughts now drift to a specific time and a specific place on its surface, a name that resonates with a quiet sense of achievement: the Sea of Tranquility. This was the destination chosen for the Apollo 11 mission in the year 1969. The name itself is beautifully calming, chosen long before any human had ever dreamed of visiting. Early astronomers, looking through primitive telescopes, saw the vast, dark, flat plains of the moon and mistook them for seas, or Maria in Latin. They gave them poetic names like the Sea of Serenity, the Ocean of Storms, and of course, the Sea of Tranquility. There was no water there, we now know, only fine, ancient dust and volcanic rock. But the name held a promise of peace, of a calm and steady place suitable for a first, tentative step. The journey itself was a marvel of careful calculation, a precise and gentle arc through the silent void between worlds. But the final moments of the descent were a quiet testament to human focus. The lunar module, named Eagle, drifted over the grey, cratered landscape. Inside, Neil Armstrong and Buzz Aldrin's attention was entirely on the world unfolding below them. The planned landing site was found to be unexpectedly rocky, scattered with boulders that could have damaged the delicate craft. With fuel running low, Armstrong took manual control, his steady hand guiding the Eagle onward, searching for a clear, smooth patch of ground. This was not a moment of high drama in the way we often think of it, but one of intense, quiet concentration. It was a moment of profound trust. Trust in the machine, trust in the training, and trust in each other. Finally, with only seconds of fuel to spare, the lander settled down upon the fine lunar soil, so gently that the astronauts inside barely felt the contact. Then came the famous words, spoken not with a shout of victory, but with the calm, steady tone of a professional completing a monumental task. "Houston, Tranquility Base here. The Eagle has landed." A world held its breath, and in that moment the Sea of Tranquility lived up to its name. It became a place of profound, accomplished peace. A few hours later, a ghostly figure in a white suit descended a simple ladder, a slow and careful process, and placed the first human footprint on another world. That first step was not a leap or a bound, but a soft, deliberate placement, a gentle touch to see if the ground was firm. It was a quiet moment that represented a monumental journey, a symbol of curiosity and the peaceful pursuit of knowledge. The world that the Apollo astronauts revealed to us was one of stark and silent beauty. The images they sent back were of a landscape painted almost entirely in shades of grey, black, and brilliant white. The sky above was not a familiar blue but a deep, unchanging black, a velvet curtain against which the distant Earth hung like a precious jewel. The sunlight there was unlike any light on Earth. With no atmosphere to scatter it, the light was direct and harsh. Shadows were not soft and diffuse, but sharp and incredibly dark, pools of pure blackness lying next to surfaces bleached by the unfiltered sun. This created a world of incredible contrast, a visual silence that matched the literal absence of sound. There is no air on the moon to carry sound waves, so it is a truly silent world. The landing of the Eagle, the footsteps of the astronauts, the deployment of experiments, all of these events occurred in a perfect, profound quiet. The only sounds were those heard inside the astronauts' own helmets. The sound of their breathing, the hum of their life support systems, and the crackle of the radio connecting them to a world 250,000 miles away. The surface itself, the regolith, was a fine, powdery dust, the result of billions of years of micrometeorite impacts pulverizing the lunar rock. It was finer than sand and softer than powder, and it clung to everything it touched. The astronauts described it as having a distinct smell like spent gunpowder, a scent that greeted them when they returned to the lunar module and removed their helmets, the fine dust having been carried in on their suits. This grey desert was punctuated by craters of all sizes, from tiny pits to vast ancient basins. These craters are the moon's memory, a physical record of its long history of cosmic collisions. They give the landscape its unique texture, its rolling hills and sudden depressions. Walking on this surface was a slow, careful dance. In the moon's gravity, which is only 1/6 that of Earth's, the astronauts felt light and buoyant, yet their bulky suits required them to move with deliberation. Every step was a conscious effort, a patient exploration of this alien, yet strangely familiar, terrain. This was the moon of our collective imagination, the world we came to know through those early missions, a place of magnificent desolation, of silent beauty, and of stark, simple landscapes under a black sky. There was a very practical and important reason why the Sea of Tranquility and the sites of the subsequent Apollo missions were chosen. They were all located in the moon's equatorial regions, the vast, relatively flat plains that face the sun most directly. For these pioneering missions, safety and simplicity were the highest priorities. The goal was to land, explore for a short time, and return safely. The equatorial plains offered the path of least resistance. They were, for the most part, geologically stable and free of the extreme terrain found elsewhere. But the most crucial factor was the sunlight. Just like on Earth, the moon's primary source of energy is the sun. The Apollo missions were timed to land shortly after lunar dawn, when the sun was low on the horizon. This provided gentle lighting that cast long shadows, making it easier for the astronauts to see craters and boulders as they navigated the final descent. More importantly, the lander and all of its systems were powered by batteries, but the sun was a critical resource. It illuminated the workspace, and its predictable path across the sky was a fundamental part of mission planning. All of the early human and robotic explorers followed this simple rule: follow the light. The sun provided visibility to navigate, warmth to moderate the cold of space, and a clear, reliable source of direction. These sunlit plains were the most welcoming and understandable places on the moon, the logical first step for a species venturing away from its home world for the first time. The challenges were already immense. There was no need to add the profound and difficult complications of darkness. The equator was the moon's gentle handshake, its most accessible and well-lit welcome mat. It was only after mastering these relatively benign environments that we could even begin to dream of the far more challenging and mysterious regions that lay hidden from progress. The sun's direct gaze. The Apollo era gave humanity a profound gift. It transformed the moon from a distant, silvery disk in the sky into a real place. A world with landscapes, with dust you could touch, and with a horizon you could stand upon. For a time, it seemed as though we had come to know the moon. We had visited its tranquil seas, collected its rocks, and planted our flags in its fine grey soil. But as the decades passed, our understanding grew, and we began to realize that the 6 small landing sites we had visited were just a tiny fraction of a vast and complex world. The moon we had seen was the moon at its most gentle, its most straightforward. The data sent back by new generations of robotic orbiters began to paint a picture of a world far more diverse and extreme than we had previously imagined. These robotic eyes mapped the entire globe, peering into craters and measuring the topography with incredible precision. They revealed towering mountains, deep, winding valleys, and most intriguingly, regions at the poles that were unlike anything we had seen before. The moon, it turned out, was not done with us. The end of the Apollo missions was not the end of the story, but merely the end of the first chapter. The moon was no longer just a destination that had been reached. It was becoming a question that was growing deeper and more complex. It held its secrets close, but it also seemed to offer them up to our patient, robotic gaze. It was a silent invitation, a cosmic whisper across the void, suggesting that there was more to see, more to learn. It was a call to return, not with the grand ambition of a race between nations, but with the quiet, persistent curiosity of a species that looks up and wonders. This quiet invitation is what underpins our journey tonight. We are moving from the moon we know, the sun-baked, equatorial plains of the past, and turning our attention toward a moon of shadows and mystery, a moon that has been waiting patiently in the wings of our understanding. We are leaving the familiar glow of the Sea of Tranquility and setting a course for the poles, where the rules of light and dark are entirely different, and where the most dangerous and wondrous places on the moon are waiting. Having bathed in the familiar light of the lunar equator, our journey now takes a turn. We guide our thoughts away from the sunlit plains and travel towards the very top and bottom of the moon. Here, at the poles, the landscape is transformed by a simple yet profound difference in the way the sunlight touches the surface. It is a realm of long shadows and islands of perpetual light, a place where the familiar rules of day and night cease to apply. This is a different moon, one that holds the key to both its ancient past and our future. For most of human history, our view of the moon has been centered on its face. We see the man in the moon, or the rabbit, familiar patterns on the side of the moon that is tidally locked to always face our planet. The Apollo missions landed on this familiar face, in the regions around its equator. But a sphere has more than just an equator. It has poles. Just as our own Earth spins on an axis that runs from the North Pole to the South Pole, so too does the moon. However, there is a critical difference. The Earth's axis is tilted by about 23.5 degrees. This tilt is what gives us our seasons. As we orbit the sun, sometimes the northern hemisphere is tilted toward it, giving us summer, and sometimes it is tilted away, bringing winter. The moon is different. Its axis is tilted by only about 1.5 degrees. It spins almost perfectly upright as it orbits the sun. This tiny, seemingly insignificant difference has profound consequences for the lunar poles. Imagine a spinning top that is wobbling significantly. A point on its side will move up and down, into and out of the light source. Now, imagine a top that is spinning almost perfectly straight up and down. A point right on its top or bottom will barely move at all relative to the light. It remains in a constant state. At the moon's equator, the sun rises high in the sky and then sets, creating the familiar cycle of a lunar day and night, though each one lasts for about 2 Earth weeks. But at the lunar poles, the sun never rises high in the sky. It never climbs overhead. Instead, it perpetually skims the horizon, forever circling the rim of the world. It is a world caught in a state of permanent sunrise, or permanent sunset. This simple fact of celestial mechanics, this tiny tilt of 1.5 degrees, changes everything. It creates an environment of extreme and permanent contrasts, a landscape carved not just by impacts and geology, but by the eternal, shallow angle of the light. It is a world of shadows that never shrink and hilltops that are almost never dark, a place entirely alien to the equatorial plains we have come to know so well. Let us try to visualize this strange polar light. Imagine standing on a vast, flat plain on Earth during the last few moments of sunset. The sun is a fiery orb resting on the horizon, and the light it casts is soft and golden. Your shadow stretches out behind you, growing longer and longer with each passing moment until it seems to go on forever. Now imagine if that sunset never ended. Imagine if the sun never dipped below the horizon, but instead just continued to circle around you, always at that same low grazing angle. This is the experience of sunlight at the lunar poles. This low, slanting light has a profound effect on the landscape. A small rock, only a few inches high, can cast a shadow that stretches for many feet. A gentle hill can create a shadow that extends for miles, a vast pool of darkness behind it. The world is not illuminated from above, but from the side. This means that visibility is strange and difficult. When looking towards the sun, the glare would be completely blinding, as there is no atmosphere to soften it. When looking away from the sun, you would be looking into a world of deep, elongated shadows. This is not the familiar interplay of light and dark that we know on Earth. Here, shadows are not fleeting things that move with the passing of the hours. At the lunar poles, the shadows are almost as permanent as the craters and mountains that create them. They do not sweep across the landscape. Instead, they slowly rotate, like the hands of a colossal clock, as the sun circles the horizon. The landscape is a stark canvas of bright, illuminated edges and deep, dark recesses. Navigating such a world would be an immense challenge. Every crater, every ridge, every boulder becomes a source of profound shadow, hiding what lies within or behind it. It is a place that would confuse the eye, a world where the normal cues of light and shadow that we use to perceive depth and distance are distorted and unreliable. This environment of long, slanting light is the first key to understanding the unique nature of the lunar poles. It is the engine that drives the creation of the most extreme places in the entire solar system, places that are just a few miles away from a sunlit peak, but have remained in darkness for longer than human beings have existed. In this world of endless, creeping shadows, there exists a remarkable and beautiful exception. While the low-angled sun plunges the crater floors into darkness, it does the opposite for the highest points of the landscape. Imagine the rim of a large crater near one of the lunar poles. This elevated ridge stands high above the surrounding terrain, as the sun circles the horizon, perpetually low in the sky. The very top of this crater rim may be just high enough to remain in its view, no matter where the sun is in its slow, circular journey. These specific elevated locations are known as peaks of eternal light. The name is slightly poetic. They are not in sunlight 100% of the time due to the occasional eclipse by the Earth or other mountains, but they are illuminated for a vast majority of the time, perhaps more than 90% of the lunar year. They are islands of near-perpetual sunlight in a polar sea of encroaching darkness. These peaks are of immense interest to scientists and engineers planning future lunar missions. In a place where sunlight is a rare and precious commodity, these illuminated mountaintops are the ultimate resource. A solar panel placed on a peak of eternal light would be able to generate a steady, reliable stream of electricity almost constantly. This is a profound advantage over the equatorial regions, where solar-powered missions must endure a 2-week-long night, shutting down or relying on powerful batteries to survive the darkness and cold. Furthermore, these peaks offer a relatively stable thermal environment. They do not experience the extreme temperature swings of the lunar equator, which can go from over 200 degrees Fahrenheit in the day to -280 at night. The constant, gentle sunlight keeps the temperatures on these peaks in a much more manageable, less extreme range. They are serene, sun-bathed sanctuaries in an otherwise harsh and challenging land. They represent a place of relative safety, a potential site for a future lunar base where humans could live and work, powered by the constant, gentle sunshine. From these illuminated peaks, we could look out and see the vast landscape of the lunar pole, with the sun forever hanging low in the sky, and below, in the deep craters, we would see the profound, unchanging darkness of their floors. Now, from those serene, sunlit peaks, our gaze drifts downward into the deep basins that they overlook. And here, we arrive at the heart of our journey. We arrive at the most dangerous, and perhaps the most valuable, places on the moon. These are the permanently shadowed regions, or PSRs. They are the perfect inverse of the peaks of eternal light. Just as the high crater rims can be tall enough to always catch the low-angled sun, the floors of some deep craters are so far down that the sun's light can never, ever reach them. The rim of the crater casts a permanent, unmoving shadow over the floor within. The sun circles the horizon, but it is always too low. Its light strikes the top of the crater wall and goes no further. The bottom of the crater remains in a state of perpetual, absolute darkness. This is not like night on Earth. Our night is softened by the reflected light of the moon and the scattered light of the stars through our atmosphere. Even a moonless, overcast night is not truly black. This lunar darkness is different. It is a profound, ancient and unbroken blackness. For billions of years, not a single direct ray of sunlight has touched the ground in these places. They have existed in a state of deep, cryogenic shadow since the time the craters themselves were formed, perhaps even since the early days of our solar system. The only illumination they have ever known is the faint, secondary glow of starlight and the even fainter reflected light from the Earth in the distant sky. The temperatures inside these craters are almost beyond comprehension. Without any sunlight to warm them, the heat has radiated away into space over the eons, leaving them unimaginably cold. Measurements from NASA's Lunar Reconnaissance Orbiter have shown that temperatures on the floor of these craters can plummet to below -400 degrees Fahrenheit or -240 degrees Celsius. These are among the coldest temperatures that have ever been measured anywhere in our solar system, even colder than the surface of Pluto, a world billions of miles farther from the Sun. This is a cold so deep that it approaches the point where molecules themselves slow to a near-perfect standstill. It is an environment more alien than anything we have yet explored directly, a place that defies our everyday understanding of temperature and darkness. These permanently shadowed craters are time capsules, pristine environments that have been sealed off from the warmth and radiation of the sun for geological ages. They are the reason why the lunar poles have become one of the most compelling destinations for future exploration. For within this profound, cold and unending night, it is believed that something incredibly precious is hiding, waiting patiently in the dark. As we pause our journey here, at the edge of one of these dark craters, it becomes clear that we are exploring a world utterly transformed from the one we visited in our first chapter. The moon of the Apollo missions, with its harsh sun, its grey dust, and its predictable cycle of a long day followed by a long night, is a world away from this polar landscape. Here, the rules are different. It is a world of eternal twilight, a place where sunlit peaks and perpetually dark craters can exist side by side, separated by only a few miles. The environment is not defined by the passing of time, but by the permanent geography of the landscape. Light and dark are not phases of a day, but features of the land, as fixed and constant as the mountains themselves. Understanding this duality is the key to understanding the allure and the danger of the lunar poles. It is a place that offers both the greatest resources, the constant solar power on the peaks, and the greatest challenges, the absolute cold and darkness of the crater floors. This polar moon is more complex, more dynamic, and far more mysterious than the equatorial plains. It has revealed itself to our robotic explorers as a place of profound scientific interest, a location that holds secrets not just about the moon itself, but about the history and evolution of our entire solar system. And it is into one of the deepest and darkest of these craters that our journey will now take us, to a specific address at the bottom of the world. We have journeyed from the familiar face of the moon to the strange twilight realm of its poles. We have seen the sunlit peaks and have now peered into the unending night of the craters below. Now, our exploration will become more specific. We will journey to a single named place, a vast basin of shadow that has become a focus of intense scientific curiosity. This is the place that embodies all the challenges and all the promise of the lunar poles. Its name is Shackleton. Our destination has a name: Shackleton Crater. It is located at the very southern pole of the moon, so precisely centered that the pole itself lies within its rim. It is a place on the edge of the world, a vast and silent amphitheater where the rules of light and shadow reach their most extreme form. Unlike many lunar craters, which are ancient and worn down, Shackleton is thought to be relatively young, perhaps only a few billion years old, and its features are still sharp and well-defined. It is about 13 miles, or 21 kilometers, in diameter and over 2.5 miles deep. Its rim is a near-continuous ring of mountains that are bathed in that near-perpetual, low-angled sunlight we spoke of earlier. They are among the moon's most prominent peaks of eternal light. But because these rims are so high, and the crater is so deep, the floor of Shackleton is cast in a permanent, profound shadow. It is one of the largest and most accessible, permanently shadowed regions on the moon. When we talk about the most dangerous place, the place where NASA will not yet land, we are talking about the floor of craters like Shackleton. It has become a symbol of this new, challenging frontier. It is a place of immense scientific interest, a location that draws our gaze and our curiosity, precisely because it is so extreme. It is not just another crater in a landscape of craters. It is a specific, known location that we have mapped from orbit, whose temperatures we have measured, and whose secrets we are patiently working to unveil. Shackleton Crater is the address of the deepest cold and the most profound darkness we know of on the moon. It is fitting that this crater, a place of extreme cold, darkness, and profound challenge, is named after Sir Ernest Shackleton, one of humanity's most renowned and resilient Antarctic explorers. His story from the early part of the 20th century is not one of triumphant arrival at a destination, but one of incredible endurance and survival against overwhelming odds. Shackleton led an expedition that intended to cross the Antarctic continent on foot. But his ship, the Endurance, became trapped and was eventually crushed by the pack ice, leaving him and his crew of 27 men stranded on the floating ice thousands of miles from civilization. The story of what happened next is a legend of leadership and perseverance. Shackleton managed to keep his men alive for over a year on the ice, before leading a small group of them on an 800-mile journey in a small, open lifeboat across the most violent and treacherous seas on Earth to the island of South Georgia. Even then, he had to cross a range of unmapped, the glacial mountains to reach a whaling station on the other side, and organize a rescue for the men he had left behind. In the end, he did not lose a single member of his crew. The name Shackleton, therefore, is synonymous with exploring the most frigid and inhospitable places on Earth and surviving. When we name a lunar crater after him, we are not just giving it a label, we are invoking this spirit of quiet, determined exploration. We are drawing a gentle parallel between the earthly poles and the lunar poles. Both are places of extreme cold, of long periods of darkness, and of profound isolation. The story of Ernest Shackleton is a human story, a reminder that exploration is not always about the destination, but about the journey and the resilience required to face the unknown. It frames our interest in this dark, cold crater not as a reckless quest, but as a continuation of a long human tradition of patiently and carefully pushing the boundaries of our knowledge, of looking at the most challenging places not with fear, but with respect and a quiet determination to understand. The name itself is a quiet nod to the immense difficulty of the task that lies ahead for any mission that dares to venture inside. Let us try to imagine the scale of Shackleton Crater. At 13 miles across, it is large enough to comfortably contain a small city. If you were to stand on one side of its sunlit rim, the other side would appear as a distant, mountainous horizon. Now, imagine looking down from that rim. The crater floor is over 2.5 miles below you. This is a depth greater than the Grand Canyon at its deepest point. The walls of the crater are incredibly steep, sloping downwards at an angle of more than 30 degrees in many places. They are a jumble of rock and lunar soil, a treacherous and unstable surface that has never been mapped in high resolution. From orbit, we can use radar and lasers to get a general sense of the crater's shape, but the fine details of its interior remain a mystery. We do not know for sure what the texture of the floor is like. Is it covered in the same fine, powdery regolith as the rest of the moon? Or is it a landscape of jagged, broken rock from the impact that formed it? Are there smaller, younger craters hidden within its deep shadow? Are its slopes prone to landslides? These are questions that can only be answered by a robotic explorer on the ground. The shape of the crater, this deep bowl with its high, steep walls, is what makes it such a perfect trap for darkness and cold. It is a natural fortress, protecting its interior from the sun's energy. Visualizing this place is an exercise in imagining absence. We must imagine a landscape where the primary sense we use to understand the world, our sight, is almost useless. It is a world that must be perceived through other means, through the gentle touch of a rover's wheels, the echo of a radar beam, or the precise measurement of a laser. The grandeur of Shackleton is not a visual grandeur like that of a sunlit mountain range on Earth. It is the grandeur of scale, of depth, and of immense silent age. It is a place that commands respect through its sheer physical presence, a giant empty bowl at the bottom of the world, holding nothing but cold, darkness, and the secrets of the cosmos. With so many craters on the moon, why has Shackleton in particular become such a focus of our attention? The answer lies in the data that has been sent back by our robotic orbiters. Instruments designed to detect the presence of certain elements have found intriguing signals coming from within Shackleton and other nearby permanently shadowed 4-dot craters. These signals are consistent with the presence of hydrogen, a key component of water. This does not mean the crater is filled with a lake or a sheet of solid ice like a skating rink. Instead, the data suggests that water ice may be mixed in with the lunar soil, perhaps as small grains of frost clinging to the regolith, or as deeper deposits buried just below the surface. The concentration of this potential ice is still a subject of debate, but the evidence is compelling enough to make Shackleton one of the most tantalizing destinations on the entire moon. This is the great allure, the reward that might justify the immense challenges of exploring such a place. That frozen water, if it exists in sufficient quantities, would be more valuable than gold. Not only is it a record of the past, but it is also the key to the future. This is why Shackleton is no longer just a feature on a map. It is a target. It is a scientific destination of the highest priority. It is a place that holds the answer to one of the most important questions in planetary science. Is there accessible water on the moon? The promise of this water has guided the design of new missions and new technologies. It has focused our collective scientific gaze upon this one specific, dark and frozen place. Our journey into Shackleton is not just a journey of idle curiosity. It is a journey with a quiet and profound purpose. We are looking for the ingredients of life, for a resource that could sustain future human explorers, and for a frozen chapter in the history of our solar system. The darkness and the cold are the guardians of this treasure, the immense natural challenges that have protected it for billions of years. And it is those challenges that we must now, gently and patiently, begin to understand. And so, our journey of the imagination brings us to the very rim of Shackleton Crater. We are standing now on one of its peaks of eternal light. The low-angled sun warms us, and the sky above is a familiar black, filled with the sharp, unblinking lights of the distant stars. Before us, the ground slopes away into a vast basin of shadow. We can see the far rim, also lit by the sun. But the floor between us is a void, a pool of unending night. We have traveled from the familiar moon to the twilight realm of the poles, and now to this specific, named place. We have learned of its scale, its history, and the great promise it holds. Now, it is time to take the next step. It is time to leave the safety of the light and begin our descent into the crater itself. We will not be exploring as humans, for the challenges are far too great. Instead, we will imagine ourselves as a quiet, robotic emissary, carefully making our way down the steep slopes and into the waiting cold. Our journey from here will be a catalogue of the great challenges that make this the most dangerous place on the moon, starting with the first and most fundamental obstacle, the profound, unimaginable cold. As we begin our gentle descent into the perpetual shadow of the crater, the first thing our robotic explorer would sense is not a feeling but an absence, the absence of warmth. The unending cold of a permanently shadowed crater is the first great barrier to exploration, a fundamental challenge that affects every aspect of a mission. It is a cold that can render machines inert and transform familiar materials into something fragile and alien. Understanding this cold is the first step in understanding why this place is so difficult to visit. The cold inside a place like Shackleton Crater is of a kind that is difficult to comprehend in human terms. It is not the biting cold of a winter's day on Earth, nor is it even the deep chill of Antarctica. It is a cosmic cold, born from the simple fact that this place has been shielded from the sun's energy for billions of years. On Earth, our atmosphere acts like a blanket, trapping heat and distributing it around the planet. Even at night, the air around us holds the warmth of the day. The moon has no such blanket. It has no atmosphere to trap or circulate heat. A surface is either in the direct path of the sun's rays or it is not. If it is in the sun, it becomes incredibly hot. If it is in shadow, it radiates its heat away into the blackness of space with nothing to stop it. In the equatorial regions of the moon, this leads to the 2-week-long frigid night. But that night is temporary. The sun always returns to warm the surface again. Inside a permanently shadowed crater, the sun never returns. The heat that was present when the crater was first formed radiated away into the void geologic ages ago, and no new heat has replaced it. The temperature has been dropping slowly and steadily for eons, until it has reached a state of equilibrium with deep space itself. The temperatures here, as we have noted, can fall below -400 degrees Fahrenheit. This is only a few tens of degrees above absolute zero, the theoretical point at which all molecular motion ceases. It is a profound, penetrating cold that is not just on the surface, but extends deep into the lunar soil. This is not a cold that comes and goes. It is a permanent feature of the environment, as constant and unchanging as the darkness itself. Any machine, any rover or lander that enters this realm must be able to survive not just a brief period of cold, but a continuous, unending bath in cryogenic temperatures. It is a thermal environment that pushes the limits of our engineering, a silent, invisible challenge that is everywhere at once. To understand what this extreme cold really means, it helps to think about what heat actually is. Heat is simply the motion of atoms and molecules. In the air we breathe, molecules of nitrogen and oxygen are zipping around at hundreds of miles per hour, constantly colliding with each other. In a warm piece of metal, the atoms are vibrating intensely in their fixed positions. The more they move and vibrate, the hotter the object is. Cold, then, is simply the slowing down of this motion. As you cool something down, its atoms and molecules move and vibrate less and less. When water freezes, its molecules lock into a rigid, crystalline structure, their movement greatly reduced. If you continue to cool that ice, the vibrations of the molecules within the crystal become slower and smaller. Now, imagine the environment on the floor of Shackleton Crater. At temperatures of -400 degrees Fahrenheit, the atomic world has become incredibly still. The molecules of water ice that we hope to find are locked in a state of profound hibernation. The atoms within any piece of rock or grain of dust are vibrating only faintly, their energy almost entirely gone. It is a world approaching a state of molecular stillness. For any robotic explorer we send there, this has enormous consequences. The lubricants and greases that we use on Earth to keep gears and joints moving smoothly would freeze into a solid, waxy substance, locking the mechanisms in place. The delicate liquid crystals in a display screen would freeze, the screen going blank forever. The chemical reactions inside a battery would slow down to a crawl, the battery unable to produce any meaningful power. It is an environment that is actively hostile to the very concept of movement and activity. It wants everything to become as still and quiet as the molecules in the frozen ground. To operate in such a place requires us to create a small, artificial bubble of warmth, a protected space where the laws of our familiar, temperate world can still apply. While just inches away, the universe is tending towards a state of perfect, frozen stillness. The deep cold of the lunar crater has another, more insidious effect on the materials we use to build our spacecraft. Many familiar materials change their fundamental properties at cryogenic temperatures. This is especially true for metals, plastics, and rubber. On Earth, we think of a material like steel as being strong and tough. You can bend it, and it will flex. You can hit it, and it will likely dent. But as you cool steel down to hundreds of degrees below zero, its molecular structure changes. It undergoes what is known as a ductile to brittle transition. The atoms become locked so rigidly in place that they can no longer slide past one another to absorb an impact. The steel loses its ability to bend and deform. It becomes brittle, like glass. A piece of steel that you could hit with a hammer in a workshop on Earth might shatter into 1,000 pieces if struck with the same force inside Shackleton crater. This same principle applies to many other materials. Rubber, used for seals, gaskets, and tires, would lose all its elasticity. It would become as hard and brittle as a piece of rock. A rubber tire on a rover would not flex over a rock. It would crack and break apart. The plastic insulation around electrical wires would become stiff and fragile. And the simple act of bending a cable could cause the insulation to crack off, creating a dangerous short circuit. Even the solder used to connect electronic components on a circuit board can become brittle and fail. This creates a profound engineering puzzle. How do you build a machine that can survive and function in a world where almost all of its components want to shatter? The solution lies in careful, meticulous material science. Engineers must select specialized alloys of metals, like aluminum and titanium, that are known to retain their ductility even at extremely low temperatures. They must use advanced polymers and composites that are specifically designed for cryogenic applications. Every single component, from the largest structural beam to the smallest wire, must be tested and certified to operate in this brittle world. It's not just about keeping the rover warm. It's about ensuring that the very materials it is made from do not betray it in the deep cold. The lander's legs must be able to absorb the shock of touchdown without fracturing. A rover's wheels must be able to roll over unseen rocks without shattering. A drill bit must be able to bore into the frozen ground without snapping. The unending cold attacks the very integrity of the machine, a silent, invisible force that seeks out any weakness in its physical form. Faced with this pervasive, unending cold, the solution is not to try and fight it head-on, but to create a small, protected sanctuary of warmth for the delicate heart of the machine. The core electronics of a lander or a rover are typically housed inside a specially designed box called the warm electronics box. This box is like a high-tech thermos, heavily insulated with layers of gold-colored foil and advanced materials to prevent the internal heat from leaking out into the frigid environment. But insulation alone is not enough. Eventually, the cold would find its way in. To counteract this, missions need a source of heat. For short-duration missions, this can be done with simple electrical heaters, but these consume a great deal of power, which is a precious resource we will soon see is incredibly scarce. For longer missions, a more reliable solution is needed. This often comes in the form of radioisotope heater units, or RHUs. These are small, simple devices, often no bigger than a flashlight battery. Inside each one is a tiny pellet of a radioactive material, plutonium-238. As this material naturally decays, it releases a steady, predictable amount of heat. It is a process that cannot be turned off and will continue for decades. An RHU is not a power source. It is simply a tiny, long-lasting furnace. By placing several of these RHUs inside the warm electronics box, engineers can create a gentle, constant source of heat that keeps the sensitive computers, radios, and instruments within their designated operating temperatures. It is a quiet, steady hum of warmth in a universe of cold. This same principle can be applied to other critical components. Small heaters can be placed near the motors in the wheels or the joints of a robotic arm to keep the lubricants from freezing. The goal is not to heat the entire rover, which would be impossible, but to strategically warm the parts that absolutely must remain functional. This approach is a delicate balancing act. The mission must have enough heat to survive, but not so much that it overheats its own electronics. It is a constant, quiet battle between the internal warmth of the machine and the profound external cold of the crater, a battle fought with layers of insulation and the gentle, persistent glow of decaying atoms. And so, we see that the extreme cold is one of the greatest dangers, a challenge that pushes our technology to its absolute limits. But as we end this chapter, it is worth looking at this cold from another perspective. For the very same cryogenic temperatures that threaten to destroy our machines are also the reason we are so eager to go there. This profound cold is a perfect preserver. On the sunlit parts of the moon, any water ice that arrives, perhaps from a comet impact, would be quickly vaporized by the sun's energy and lost to space. But inside the permanent shadow of the crater, the story is different. The cold is so deep that it acts as a cosmic freezer, a cold trap. Any water molecule that happens to find its way into the crater, whether from a comet, an asteroid, or from the solar wind, will immediately freeze onto the lunar soil and become trapped. The temperature is so low that the ice can never sublimate or turn directly from a solid into a gas. It is locked in place, unable to escape. This means that the ice we hope to find there could be billions of years old, a pristine, frozen sample of the materials that were present in the early solar system. The cold, therefore, is not just a hazard, it is a promise. It is the guardian of the very prize we seek. It is the reason the darkness holds such immense scientific value. And so, having understood the challenge of the cold, we must now turn our attention to its constant companion, the second great challenge of this dangerous place, the absolute, unending dark. Having felt the profound cold that permeates the crater floor, our attention now shifts to the other defining characteristic of this environment. It is a challenge not for the materials of our robotic explorer, but for its very lifeblood, its energy. We now enter the second great challenge, the absolute and perpetual darkness, a darkness that has profound implications for how any mission can be powered and how it can possibly see where it is going. The darkness inside a permanently shadowed crater is more than just the absence of sunlight. It is a fundamental state of being for that place. As we have learned, this darkness is ancient, a condition that has persisted for geological eons. It is a darkness that has witnessed the slow, steady rain of micrometeorites, the occasional impact of a larger body, and the gradual accumulation of any volatile molecules that have found their way into its cryogenic embrace. To be on the floor of Shackleton Crater would be to stand in a place that has never known a sunrise. The very concept of day has no meaning here. The blackness is not a temporary phase in a cycle, but a permanent, unchanging feature of the landscape. This has a powerful, almost philosophical quality to it. It is a piece of the original, primordial darkness of the cosmos, preserved right here in our own cosmic neighborhood. On Earth, our darkest nights are still filled with the faint glow of our atmosphere, the light of distant cities, and the shimmer of the stars. In this lunar crater, there is no atmosphere to scatter light, and the towering crater walls would block out much of the sky. The darkness would be profound, a deep and enveloping blackness that the human eye is not equipped to handle. But for a robotic mission, the primary consequence of this darkness is not a matter of sight, but of survival. The vast majority of spacecraft that we have sent to explore the solar system have relied on a single, abundant source of power, the sun. From the earliest satellites to the rovers on Mars and the probes orbiting Jupiter, we have used solar panels, large, wing-like structures covered in photovoltaic cells to convert sunlight into electricity. This method is reliable, well understood, and once the spacecraft is launched, the fuel is essentially free. It is the standard default way we power our journeys through the cosmos. In the unending night of a permanently shadowed crater, this entire approach is impossible. A rover equipped with even the most efficient solar panels ever designed would be completely inert, unable to generate a single watt of power. The darkness is not just a visual obstacle. It is a power desert, an environment bereft of the energy that sustains almost all of our other explorations. To enter this realm is to leave behind the single most important resource for space travel, and to face the challenge of surviving without the sun. For a machine on the floor of Shackleton Crater, the sun, the center of our solar system, the source of all our light and warmth, is reduced to being just another star in the sky, and not even a visible one. It is forever hidden behind the crater rim, its immense energy completely cut off. This forces a fundamental rethinking of how a mission can be designed. The familiar image of a spacecraft with its magnificent solar wings spread wide is irrelevant here. Any mission to the surface of a permanently shadowed region must carry its own source of power, one that is entirely independent of sunlight. This dramatically increases the complexity, the cost, and the mass of the mission. The simplest solution is batteries. A lander could be equipped with a large set of batteries, charged up before it leaves Earth, that would power it for a short-duration mission. It could land, perform its tasks for a few hours or a few days, and then, when its batteries are depleted, its mission would be over. It would become another silent, frozen monument on the lunar surface. This is a viable strategy for a short, targeted mission, a quick look into the darkness. But if we want to do more, if we want to explore for weeks, months, or even years, to traverse the crater floor and drill into its icy soil, then batteries alone are not enough. The energy requirements for moving a rover, operating a drill, running scientific instruments, and communicating with Earth are substantial. A battery-powered mission would be over almost as soon as it began. The absolute darkness, therefore, forces us to look beyond the simple solutions and towards more advanced, more complex, and more challenging forms of power generation. It fundamentally changes the calculus of exploration. It means that a mission to this most dangerous place cannot be a simple one. It must be robust, self-sufficient, and capable of generating its own lifeblood in a place where the universe provides none. The absence of the sun is an absence of energy, and in the cold, unforgiving environment of space, an absence of energy is an insurmountable obstacle unless you bring your own. Is the darkness inside these craters truly absolute? The answer, in a strict scientific sense, is no. While no direct sunlight ever reaches the floor, there are other, incredibly faint sources of light. The primary one is starlight. The distant suns of our galaxy cast their ancient light across the cosmos, and some of it will find its way into the crater. Another source is reflected light from the sunlit crater rim opposite the sun. This is similar to how, on Earth, a bright, sunlit wall can cast a soft glow into a shaded alleyway. This reflected light would be incredibly weak, a mere ghost of the brilliant sunshine just a few miles away. Perhaps the most significant secondary light source, however, is Earthshine. From the perspective of the Moon's south pole, the Earth does not rise and set, but instead hangs low in the northern sky, slowly rotating. Our planet, with its bright clouds and vast blue oceans, is highly reflective. The sunlight that strikes the Earth is reflected back out into space. And some of this reflected light, this Earthshine, would travel across the 250,000-mile gap and fall into the darkness of Shackleton Crater. So, the floor of the crater is not a perfect, featureless black. It is bathed in a ghostly, ethereal glow, a light many thousands of times dimmer than a moonlit night on Earth. This light is far, far too weak to be used for solar power. A solar panel would not even register its presence. It is also likely too dim for a conventional camera to see much of anything, though a highly sensitive, long-exposure camera might be able to capture a faint, grainy image of the landscape. While this faint light is a beautiful and poetic idea, the darkness of the moon being softly illuminated by the light of its home world. It does not solve any of the practical problems of exploration. In fact, it can create new ones. This faint, diffuse glow, coming from multiple directions at once, would not create any sharp shadows. It would be a flat, low-contrast light that could make it even more difficult for a rover's navigation systems to perceive depth and identify obstacles. The gentle darkness, therefore, remains one of the most profound challenges. It is not quite absolute, but it is so close as to make no difference for power, and its faint, ghostly illumination might be more of a hindrance than a help for seeing. If solar power is impossible and batteries are too limited, how can we possibly power a long-term mission in the perpetual dark? The answer lies in the power of the atom. For decades, NASA has used a technology called a radioisotope thermoelectric generator, or RTG, to power its most ambitious missions to the outer solar system, far from the sun. This technology is a close cousin to the small heater units we discussed earlier, but it is designed to generate electricity. An RTG contains a larger amount of plutonium-238, a non-weapons grade, specially produced isotope of plutonium. As the plutonium decays, it generates a significant amount of heat. This heat is allowed to radiate across a set of devices called thermocouples. A thermocouple is a simple, solid-state device made of two different types of metal joined together. When one side of the thermocouple is hot and the other side is cold, a small electrical voltage is created. An RTG contains hundreds of these thermocouples, with their hot side facing the plutonium heat source and their cold side facing the frigid environment of space. The temperature difference between the hot interior and the cold exterior generates a steady, reliable flow of electricity. An RTG is a form of nuclear power, but it is not a nuclear reactor. There is no fission, no chain reaction. It is more like a nuclear battery, one that uses the predictable, slow decay of a radioactive element to generate power for decades. The Cassini spacecraft that orbited Saturn, the Voyager probes that are now in interstellar space, and the Curiosity and Perseverance rovers on Mars, all have been powered by RTGs. This technology is our only proven method for conducting a long-duration, high-power mission in the darkness of a lunar crater. A rover equipped with an RTG would have a constant, reliable source of electricity day and night because there is only night. It would have the power to run its motors, to operate its drill, to keep its electronics warm, and to send its precious data back to Earth. However, RTGs are complex and expensive to produce. The plutonium they use as fuel is rare and requires specialized facilities to create. Designing a mission around an RTG is a major undertaking, reserved for the highest priority scientific quests. The absolute darkness of the lunar crater, therefore, forces us to consider this most advanced and robust of power systems. It is the steady, reliable heartbeat that could allow a machine to not just survive, but to thrive in a place where the sun never shines. We have now established a way for our robotic explorer to stay warm and powered in the unending cold and dark. It has a warm electronic heart, protected by insulation and heaters, and it is powered by the steady decay of a nuclear battery. It can survive. But how can it move? How can it explore a landscape that it cannot see? The faint, ghostly glow of starlight and earthshine is not enough for safe navigation. A rover cannot simply turn on a pair of headlights, like a car at night. The fine lunar dust would scatter the light, creating a blinding glare, and the headlights would only illuminate a tiny patch of ground just in front of the rover, leaving the wider terrain a complete mystery. To land safely and to traverse the unseen floor of the crater requires a different way of perceiving the world. It requires a way of seeing without sight. This leads us directly to the third great challenge of this dangerous place: the profound difficulty of navigating a landscape of absolute, featureless shadow, a world that has never been mapped in detail, and where every step is a step into the unknown. Our robotic explorer is now equipped with warmth and power, a resilient machine ready to face the extreme environment. But a machine that cannot move or cannot move safely is of little use. The third great challenge is one of perception and movement. How does a spacecraft land in a place it cannot see? And how does a rover drive across a surface that is hidden in near-perfect darkness? This is the challenge of navigating the unseen. The process of landing a spacecraft on another world is one of the most complex and difficult parts of any mission. It requires incredible precision and a constant stream of information about the spacecraft's altitude, speed, and the terrain below. For the Apollo missions and the Mars rovers, the final phase of the landing was guided by a combination of radar and optical cameras. The lander could look down and see the surface, identifying large boulders or steep slopes, and its automated systems, or in Apollo's case, a human pilot could adjust the final touchdown point to ensure a safe, level landing. In the perpetual darkness of a polar crater, this is not possible. There is nothing for a standard camera to see. The lander is descending into a visual void. This means that the entire landing sequence must be accomplished blind. The spacecraft must rely entirely on instruments that can perceive the world without light. The foundation of such a landing is radar. The lander would be constantly sending radio waves down to the surface and listening for the echoes. By measuring the time it takes for the echoes to return, it can calculate its altitude with great accuracy. A more advanced system, known as a radar altimeter and velocimeter, can use the Doppler effect of these echoes to determine its horizontal and vertical speed as well. This provides the basic information needed to control the descent. However, this only tells the spacecraft how far away the ground is. It doesn't say anything about the condition of that ground. Is it a smooth, flat area, or is it the side of a steep crater wall or a field of sharp rocks? To solve this, the mission must rely on maps made before the landing even begins, using data from orbiters like the Lunar Reconnaissance Orbiter, which has used lasers to map the moon's topography. Mission planners would create a detailed digital elevation map of the intended landing zone. This map would be preloaded into the lander's computer, giving it a picture of the world it is about to enter. The landing becomes an exercise in pure trust in the data, a descent guided by a map of a world that no one has ever seen directly. While preloaded maps are essential, they may not be detailed enough to show smaller, mission-threatening hazards. A rock the size of a coffee table would be invisible from orbit, but it could be large enough to damage the lander or cause it to touch down at a dangerous angle. To overcome this, the lander needs to be able to make its own map in real time during the final moments of its descent. This is accomplished with a technology called LiDAR, which stands for light detection and ranging. LiDAR works on the same principle as radar, but it uses pulses of laser light instead of radio waves. The lander's computer would fire tens of thousands of tiny invisible laser pulses down at the surface every second. By measuring the return time of each pulse, it can build up an incredibly detailed, three-dimensional map of the ground below. It is essentially painting the unseen landscape with light, creating a precise picture of every rock and every slope in the landing zone. This technology is at the heart of what is known as terrain relative navigation. The lander's computer would compare the real-time LiDAR map it is building with the preloaded orbital map already in its memory. By matching the features, it can determine its own position with pinpoint accuracy, to within a few feet. If the computer sees that its current trajectory is taking it towards a hazardous area, a steep slope or a large boulder identified by the LiDAR, it can fire its thrusters to divert itself and navigate to a safer, pre-selected landing site nearby. This is not a simple process. It is a high-speed, autonomous dance of light and echoes. The lander must build the map, understand the terrain, recognize the hazards, and command its engines to adjust its path, all in the final, critical seconds before touchdown. It is a system that allows the spacecraft to have eyes, even in the complete darkness, to see the shape of the world not with reflected ambient light, but with its own self-generated perception. Once our mission has landed safely on the crater floor, the challenge of navigation is transferred to the rover. The rover now has to do something arguably even more difficult: drive across a surface that has never been mapped in high detail. While our orbital maps might show us the large-scale slopes of the crater, they cannot show us the smaller rocks, the soft patches of dust, or the hidden crevasses that could trap a rover forever. The rover, just like the lander, must be able to perceive the world on its own. It too would likely use a combination of LiDAR and other sensors to build a 3D map of its immediate surroundings. The process would be slow and methodical. The rover might drive for a few feet, then stop. It would then scan the area ahead of it, building a detailed map of the terrain. Its autonomous navigation software would analyze this map, identifying the safest path forward, a path that avoids steep inclines and large obstacles. Then, it would proceed along that path for another few feet, and the process would repeat. Every step would be a careful, considered one, a gentle advance into the unknown. This is very different from how we have operated rovers on Mars. On Mars, with its bright sunlight, we can take pictures of the landscape, send them back to Earth, and have human operators plot a course for the next day's drive. In the darkness of a lunar crater, this would be incredibly inefficient. The rover must have the intelligence to make many of these decisions on its own. Human operators would still be in the loop, setting the overall goals and checking the rover's progress. But the moment-to-moment, step-by-step navigation would have to be handled by the machine itself. The rover becomes a cautious, blind explorer, tapping its way through the darkness with beams of laser light, moving with a slowness that speaks to the profound respect it must have for the unseen dangers of the terrain around it. The terrain itself presents a unique set of challenges. The floor of an impact crater is not necessarily a smooth, flat plane. The colossal energy of the impact that formed it would have shattered the bedrock, throwing up a jumble of debris. The landscape could be a mix of that fine, powdery regolith we expect on the Moon, and fields of sharp, angular rocks of all sizes. The slopes of the crater walls themselves are a major hazard. At over 30 degrees, they are far too steep for a rover to climb safely. Any exploration would likely be confined to the relatively flatter areas of the crater floor. Even on the floor, however, there could be smaller, younger craters hidden in the darkness. A rover driving blindly could easily find itself on the rim of a steep depression, with the risk of tipping over or getting stuck. The nature of the soil, or regolith, is another unknown. It has been in a deep freeze for billions of years. Is it soft and loose, like the dust at the Apollo sites? Or has the potential presence of ice cemented it together into a hard, rigid surface? A rover's wheels are designed for a specific type of terrain. If the ground is too soft, the wheels could dig in, and the rover could become hopelessly bogged down, like a car stuck in deep sand. If the ground is too hard and rocky, the wheels could be damaged by the sharp edges of the rocks. Without the ability to see the terrain ahead, the rover must rely on its engineering to handle whatever it encounters. Its wheels might be made of a flexible metal mesh, designed to conform to the shape of rocks without breaking. Its suspension system would need to be robust enough to handle the jolts of unseen obstacles. The rover must be designed to be physically resilient, a sturdy and sure-footed explorer capable of withstanding the shocks and surprises of a landscape it can only feel its way through. Every movement is a risk. Every gentle step forward, a potential encounter with a mission-ending obstacle that has been waiting in the dark for eons. So we can see that navigating the unseen is not about finding a single magical solution. It is about building layers of perception. It begins with the maps we make from orbit, our first large-scale sketch of the world. Then, it is refined by the real-time, precise mapping of a lander's LiDAR as it makes its final descent. And finally, it is continued by the slow, careful, step-by-step scanning of a rover as it feels its way through the darkness. The entire process is a conversation between the machine and the landscape, a conversation held not in words or images, but in the silent, invisible whispers of laser pulses and radar echoes. The map of this new world is built one data point at a time, a patient and meticulous act of listening to the shape of a place that cannot be seen. But there is another layer to this isolation. Even if our rover can see with lasers and move carefully through the dark, it is of no use if it cannot share what it finds. This brings us to the fourth great challenge, the profound and isolating silence of a world cut off from home. Our robotic explorer has now landed safely and is moving cautiously across the crater floor. It is warm, it has power, and it can perceive the world around it through a sense of digital touch. but exploration is a two-way street. A machine that cannot communicate, cannot send back its discoveries or receive new instructions, is merely a lost piece of technology. The fourth great challenge is one of connection, of maintaining a link to home from a place that is naturally designed to be isolated and silent. The fundamental principle of most space communication is simple. You need a direct, unobstructed line of sight between your transmitter and your receiver. On Earth, we use a network of tall radio towers and satellites in orbit to bounce signals around the curve of the planet. In space, communication is often simpler. To talk to a rover on Mars, we wait until the Earth and Mars are on the same side of the Sun, and we point a large radio dish, a transmitter, at the rover. The rover in turn points its antenna, a receiver, back at the Earth. As long as there is nothing in between, the signal can travel across the millions of miles of empty space. This is how we have communicated with our probes across the solar system for decades. This simple, fundamental rule of line-of-sight communication is what creates the profound challenge inside a deep lunar crater. An explorer on the floor of Shackleton crater is over 2 miles deep inside a bowl of rock. From its perspective, the Earth, which hangs low in the northern sky, is permanently hidden behind the towering northern rim of the crater. There is no moment, no time of day or year, when the Earth will ever rise above that rim. The line of sight is permanently and completely blocked. This means that direct communication between the rover and the Earth is impossible. It is like trying to make a phone call to someone on the other side of a mountain. The signal simply cannot pass through the solid rock. The rim of the crater is more than just a physical barrier. It is a wall of silence. It creates a cone of silence that isolates the crater floor from the rest of the universe. Any radio signal our rover sends out will travel up, hit the crater wall, and either be absorbed or scattered in a random direction. No coherent message can escape. Likewise, any command sent from mission control on Earth will strike the outside of the crater and never reach the rover deep within. This creates a situation of profound isolation. A rover on the crater floor would be more alone than any explorer in human history. The Mars rovers, even on the far side of the planet, are only ever a few hours away from being able to communicate with Earth as the planets rotate. An explorer in Shackleton crater, without a specialized solution, would be cut off forever. This has enormous implications for how a mission would operate. There can be no real-time control, no joysticking of the rover by a human operator. There can be no immediate intervention if something goes wrong. A rover that encounters an unexpected problem cannot simply stop and ask for help. It would be on its own, left to solve the problem with its own onboard intelligence or to follow a pre-programmed set of instructions. This isolation also means that the precious scientific data, the measurements of the icy soil, the images from its microscopic camera, the very discoveries the mission was sent to make would be trapped along with the rover. The data would be collected and stored in the rover's memory, but there would be no way to send it home. It would be like a library filled with priceless books, but with its doors locked forever. The wall of stone that creates the darkness and the cold also creates this profound, isolating silence. To overcome this, we cannot simply build a more powerful transmitter. The problem is not the strength of the signal, but the fundamental geometry of the landscape. We must find a way to bypass the wall, to create an artificial bridge for our communications that can leap over the crater rim. The solution to the problem of line-of-sight communication is as elegant as it is simple in concept. If you cannot see around an obstacle, you must go over it. In this case, that means using a relay. The most straightforward way to do this is with a dedicated communications orbiter. We would place a satellite in a carefully chosen orbit around the Moon, an orbit that takes it directly over the South Pole. This satellite would act as a celestial messenger, a bent pipe for our radio signals. The rover on the crater floor would not point its antenna towards the distant, hidden Earth. Instead, it would point its antenna straight up and wait for the relay orbiter to pass overhead. When the orbiter is in view, the rover would transmit its data package, its scientific findings, its health status, and any pictures it has taken. The orbiter would receive this signal, and then, as its own orbit brings it into line of sight with the Earth, It would turn its own antenna towards our planet and retransmit the message. In the same way, commands from mission control would be sent up to the orbiter, which would then store them and forward them down to the rover the next time it passes overhead. This relay system effectively creates a bridge of communication over the crater wall. It allows us to talk to a place that is naturally silent. However, it also introduces a new set of complexities. A single orbiter in a low lunar orbit might only be in view of the rover for a short period of time, perhaps only a few minutes during each orbit. This means that communication would not be continuous. There would be long periods of blackout, followed by short windows of communication. During the blackouts, the rover would once again be on its own, carrying out its tasks autonomously. The mission would become a slow, patient rhythm of exploration and communication, of long, silent work followed by a brief, upward burst of data. To achieve more continuous communication, a more complex system is required. A single relay orbiter provides only intermittent contact. For a human mission, or a highly complex robotic one, this might not be enough. The solution is to create a network, a chain of whispers that can guarantee a constant link. One concept involves placing multiple satellites into a carefully choreographed orbital dance. For example, a constellation of 3 or 4 satellites in a specific type of polar orbit could be arranged so that, from the rover's perspective on the crater floor, at least one of them is always visible in the small patch of sky overhead. As one satellite is about to set behind the crater rim, another one is already rising, ready to take over the communication link. This would provide a continuous, unbroken connection to Earth, allowing for more complex operations and a greater sense of safety. However, launching and maintaining a constellation of multiple satellites is a significant undertaking, adding to the cost and complexity of the overall mission architecture. Another intriguing idea is to use the landscape itself as part of the solution. Instead of relying solely on orbiters, we could place a stationary relay station on a high point of the crater rim, one of the peaks of eternal light. This relay lander would have a commanding view of both the crater floor below and the Earth in the sky above. It would also have access to near-constant solar power. The rover on the floor would send its signal on a short, easy hop up to the rim station. The rim station would then use its larger, more powerful antenna to send the signal on the long-haul journey back to Earth. This creates a robust and reliable communication hub. It is a simpler solution than a multi-satellite constellation, but it requires its own separate landing on the treacherous, mountainous terrain of the crater rim. Each approach has its own trade-offs, its own intricate ballet of geometry and timing. But they all share a common goal: to overcome the natural isolation of the crater and to ensure that the whispers of discovery from that cold, dark place can find their way home. No matter which relay system is used, one fact remains. A rover in a polar crater will experience periods of isolation. Whether it is for a few minutes or a few hours, there will be times when it is completely on its own. This demands a high degree of autonomy. The rover's software must be sophisticated enough to manage its own resources, to navigate the terrain safely, and to handle unexpected events without human intervention. What if a wheel gets stuck? What if a scientific instrument returns a strange reading? What if it detects that its power levels are dropping unexpectedly? The rover must be able to diagnose these problems and enter a safe mode, a state of hibernation where it conserves energy and waits for the next communication window to ask for help. This is the loneliness of the machine. It is a quiet, self-reliant explorer, designed to be both intelligent and resilient. It is a testament to the trust we must place in our own engineering, sending a machine to a place we cannot see, to perform tasks we cannot directly supervise, in a silence we can only break with a carefully planned chain of celestial whispers. Having now understood the challenges of cold, dark navigation and communication, it is time to turn our attention to the reward, the great prize that makes overcoming these immense obstacles a worthy endeavor. We have journeyed through a gauntlet of immense challenges. We have felt the deep, material-shattering cold, navigated the absolute dark, and contemplated the profound, isolating silence. The question that naturally arises is, why? Why would we even attempt to go to such a difficult and dangerous place? The answer is simple and profound. It is the allure of the ice. The very same conditions that make these craters so hostile are also what make them a treasure chest of cosmic history and a vital resource for the future of beating, exploration. The concept that underpins the great reward of the polar craters is known as a cold trap. It is a simple and elegant idea. Imagine a molecule of water, H2O, floating through the vacuum of space near the moon. If this molecule strikes a part of the lunar surface that is lit by the sun, the energy from the sunlight will quickly heat it up. This gives the molecule enough energy to bounce off the surface and continue its journey through space. The sunlit parts of the moon are too warm for water to stick around. Now, imagine that same water molecule, by pure chance, happens to drift into the opening of a permanently shadowed crater. As it travels down into the darkness, it eventually strikes the frozen ground. The temperature of this ground is so incredibly low, below -400 degrees Fahrenheit, that the water molecule instantly freezes onto it. It becomes a tiny grain of frost clinging to the lunar soil. Because there is no sunlight, the molecule never receives enough energy to escape again. It cannot sublimate and turn back into a gas. It is trapped. The crater floor acts like a celestial flypaper for water molecules. Over billions of years, this process has been happening continuously. Any volatile molecule, not just water, that finds its way into one of these cold traps is likely to stay there. This means that these craters have been slowly and patiently accumulating a frozen record of the materials that have been delivered to the moon over its long history. They are natural collection bins, preserving a sample of the cosmic environment in a pristine, deep frozen state. The cold that is such a great challenge for our technology is also the very mechanism that creates this incredible scientific opportunity. It is a perfect, natural laboratory for planetary science, one that has been running an experiment for eons, and we are just now developing the tools to go and read the results. The cold trap is the scientific heart of the matter, the simple physical principle that transforms a dark, cold crater from a desolate wasteland into one of the most valuable pieces of real estate in the solar system. If the craters are the collection bins, where did the water come from in the first place? The leading theory is that it was delivered to the moon by a slow, steady rain of comets and water-rich asteroids. Comets are often described as dirty snowballs. They are leftover building blocks from the formation of the solar system, composed of a mix of rock, dust, and a large amount of frozen water and other volatile compounds like methane and ammonia. For billions of years, the inner solar system has been a kind of cosmic shooting gallery, with comets and asteroids occasionally colliding with the planets and their moons. When a comet strikes the moon, the incredible energy of the impact vaporizes the comet's ice, creating a vast cloud of water vapor. This cloud expands out from the impact site. Many of those water molecules are lost to space, but a small fraction of them will travel across the lunar surface. By chance, some will drift into the cold traps of the permanently shadowed craters at the poles, where they will freeze and become a permanent part of the lunar soil. This process has been repeated countless times over the age of the solar system. Each comet impact is like a brief, violent river, delivering its cargo of ancient water to the lunar environment. Another potential source of this water is the solar wind. The sun is constantly streaming a flow of charged particles, mostly protons, which are the nuclei of hydrogen atoms. When these protons strike the lunar soil, which is rich in oxygen, they can, over long periods, combine to form molecules of water. This is a much slower process, but it is a constant one. It is likely that the water ice we hope to find is a combination of these two sources. A baseline of water created by the solar wind, punctuated by richer deposits delivered by ancient comets. This paints a serene and beautiful picture of the moon's history, one where the ingredients for life are not created on the moon, but delivered from the cosmos, and then patiently collected and preserved in the silent, dark vaults of its polar craters. The scientific value of this ice is almost impossible to overstate. Because it has been preserved in a deep freeze for potentially billions of years, it is a pristine sample of the early solar system. It is a frozen, undisturbed record of the cosmic chemistry of a bygone era. By drilling into this ice and analyzing its composition, we could learn incredible things. The ice from comets, for example, would contain not just water, but also other organic molecules, the carbon-based building blocks of life. Studying these molecules could give us clues about the origin of life on Earth. It is widely believed that comets delivered much of the water and organic material to our own planet, seeding it with the ingredients necessary for life to arise. The ice on the Moon could be a perfectly preserved sample of those very same ingredients, a window into the chemistry that led to our own existence. Furthermore, the ice may not be a uniform mixture. It is possible that it is laid down in layers, like the layers of ice in a glacier on Earth. Each layer would correspond to a different period in the Moon's history. By drilling a core sample and analyzing these layers, we could read the history of the solar system like the rings of a tree. We might be able to identify a layer from a period of heavy cometary bombardment, or see changes in the composition of the solar wind over time. The ice could also contain trapped gases from the ancient lunar atmosphere, which the Moon had briefly after its formation. The isotopes within the water molecules, the different flavors of hydrogen and oxygen, can tell us where in the solar system that water originated, whether from the inner or outer regions. This frozen ground is more than just a resource. It is an archive. It is a library of cosmic history, written in the language of chemistry and frozen in time. Accessing this library has been a dream of planetary scientists for decades. It would be like finding a perfectly preserved fossil of the early solar system, a direct link to the conditions that existed when the planets themselves were young. This is the profound scientific reward, the promise of knowledge that calls to us from the cold and the dark. Beyond the immense scientific value, the lunar ice has a second, equally important allure. It is a practical, tangible resource that could fundamentally change the future of human space exploration. The single most expensive and difficult part of space travel is lifting mass out of Earth's powerful gravity well. Every pound of water, air, or fuel we send into space costs an enormous amount of money and energy. If we could find and use the resources that are already in space, a concept known as in situ resource utilization, or ISRU, it would make all future exploration dramatically easier and more sustainable. Water is the key to this entire vision. The most obvious use for it is for life support. Future astronauts living on the Moon could drink the water, use it to grow food in greenhouses, and use it for sanitation. This would drastically reduce the amount of material they would need to bring with them from Earth, allowing for longer and more ambitious missions. But the true value of water lies in its constituent elements, hydrogen and oxygen. By passing an electric current through water, a simple process called electrolysis, we can split the H2O molecule into pure hydrogen and pure oxygen. The oxygen can be used to create breathable air for a lunar habitat. The hydrogen and oxygen, when combined, are also the most powerful and efficient chemical rocket propellant we know of. This means that a lunar base located near the polar ice could, in theory, become a cosmic refueling station. We could launch rockets from Earth with just enough fuel to get to the Moon, and then refuel them there for journeys to more distant destinations like Mars. The Moon would be transformed from a simple destination into a stepping stone, a gateway to the rest of the solar system. The polar ice is the wellspring that could enable this entire future. It is the resource that could allow us to move from short, flag-planting missions to a sustained, long-term human presence in space. And so, we see the dual nature of the great reward that lies waiting in the darkness. On the one hand, the ice is a look backward, a frozen record of the ancient past that can tell us about the history of our solar system and perhaps even the origin of life. On the other hand, it is a look forward, a vital resource that could unlock a future of sustainable human exploration, a wellspring for a new age of discovery. This is the gentle promise of the polar craters. It is the reason we are willing to face the immense challenges of the cold, the dark, the navigation, and the communication. The allure of the ice is the allure of knowledge and the allure of the future, combined in one pristine frozen deposit. But as our understanding has grown, we have come to realize there is one final, subtle, and pervasive challenge that we have not yet considered. a challenge that is as microscopic as the crater is vast. The clinging, abrasive nature of the lunar dust. We have explored the grand cosmic challenges of the lunar poles. The profound cold, the absolute dark, the unseen terrain, and the isolating silence. Now we must turn our attention to a fifth and final challenge, one that is more subtle, but no less formidable. It is the challenge of the lunar dust, or regolith. This fine, abrasive powder is everywhere on the moon, and in the unique environment of a permanently shadowed crater, it presents a unique and persistent threat to any machine we send there. The dust on the moon is fundamentally different from the dust we are familiar with on Earth. On our planet, dust is the product of erosion. The forces of wind and water constantly wear down rocks, tumbling them against each other, smoothing off their sharp edges, and breaking them down into small, rounded, and relatively soft particles. This is why sand on a beach or dust in a desert is generally not harmful to machinery, other than by getting into moving parts. The moon has no wind and no liquid water. There is no erosion as we know it. The lunar regolith was created by a different process, billions of years of bombardment by micrometeorites. For eons, the lunar surface has been struck by a constant fine spray of tiny, high-velocity particles from space. Each impact, no matter how small, releases a burst of energy that melts and shatters the rock, creating tiny, glassy, and incredibly sharp particles. The lunar dust is not like soft sand, it is like microscopic, broken glass. The individual grains are angular, with jagged edges. Under a microscope, they look like tiny shards of shrapnel. The Apollo astronauts discovered firsthand how difficult this dust could be. It was incredibly abrasive. It wore away at the layers of their spacesuit boots. Like sandpaper, it clogged the mechanisms of their tools and scientific instruments. When they brought it back inside the lunar module on their suits, it got everywhere. It floated in the zero-gravity environment, causing irritation to their eyes and lungs. They described it as a constant nuisance, a fine, gritty powder that was impossible to get rid of. Any mission to the lunar poles, robotic or human, must contend with this same abrasive material. But in the darkness of the crater, the problem is compounded. A rover or lander cannot see where the dust is accumulating, and it has no easy way to clean itself. The dust becomes a silent, ever-present, abrasive force, constantly seeking to wear down and infiltrate the delicate workings of the machine. Now, let us place this abrasive, glassy dust into the environment of a permanently shadowed crater. Here, it is not just a nuisance, it is a major engineering challenge. A rover driving across the crater floor will constantly kick up this dust with its wheels. In the absence of an atmosphere, the dust will not form a swirling cloud that settles quickly. Instead, it will be thrown up in a wide, slow-moving arc, a phenomenon observed during the Apollo missions. This means that the rover will be constantly driving through a self-generated spray of microscopic, abrasive particles. This dust will settle on every surface, on its camera lenses if it has them, on its solar panels, if it were in the light, on its antennas, and most critically, on its moving parts. The joints of a robotic arm, the motors that drive the wheels, the mechanism of a drill, all of these are vulnerable. The fine, sharp dust can work its way into the smallest gaps, getting into bearings and gears. Once inside, it acts like a grinding paste, slowly but surely wearing away at the metal until the mechanism fails. The process of drilling for the water ice we seek is particularly vulnerable. A drill bit must spin at high speed and press down into the frozen regolith. This action will inevitably generate dust and debris. How do you prevent this dust from clogging the drill mechanism itself? How do you collect a clean, uncontaminated sample of the ice when it is surrounded by this abrasive powder? These are complex problems that require clever engineering solutions. Perhaps the drill would be shielded, or it might use a blast of nitrogen gas to blow the dust away as it works. But every solution adds complexity and mass to the mission. The dust is a silent, creeping threat. It does not cause a sudden, catastrophic failure, but rather a slow, grinding degradation of the machine's ability to function. In the unseen depths of the crater, The rover is wading through an invisible abrasive sea that constantly seeks to wear it down. There is another property of the lunar environment that makes the dust even more problematic: static electricity. On Earth, our humid atmosphere helps to dissipate static charge. On the airless moon, this does not happen. The lunar surface is constantly bombarded by the solar wind and by ultraviolet radiation from the sun. This can knock electrons off the dust particles, giving them a strong, positive electrical charge. This is why the dust clings to everything it touches with a powerful static cling, far stronger than the static electricity we might experience on a dry winter day. The Apollo astronauts found that simply brushing the dust off their suits was almost impossible. It stuck to the fabric as if it were magnetized. This electrostatic charging also causes a strange and beautiful phenomenon known as dust levitation. At the terminator, the line between lunar day and night, the charged dust particles can actually lift off the surface and float, suspended by electrical fields, creating a hazy, glowing horizon. While the floor of a permanently shadowed crater is shielded from the direct solar wind, it is still in a complex plasma environment. The dust there is also expected to be electrically charged. This means that the fine, abrasive particles will not just settle on the rover, they will actively cling to it. They will stick to the surfaces of radiators, preventing them from properly shedding the rover's waste heat. They will coat antennas, potentially interfering with the vital communication link to the relay orbiter. They will work their way into seals and connectors with a stubborn persistence. This combination of being both highly abrasive and electrostatically sticky makes lunar dust a uniquely difficult material to handle. Engineers must design systems that are not just resistant to abrasion, but also able to mitigate the effects of this powerful static cling. This might involve using special conductive coatings on surfaces to help dissipate the charge, or designing covers and seals that create a positive pressure environment, actively pushing the dust away from sensitive components. Given the pervasive threat of the lunar dust, a key part of designing any mission is a strategy for dust mitigation. This is not about a single solution, but a philosophy of protection that must be built into every aspect of the machine. It starts with shielding the delicate heart of the rover. All sensitive components, from the main computer to the scientific instruments, are housed within sealed enclosures. These enclosures use advanced gaskets and knife-edge seals, designs borrowed from vacuum technology on Earth, to create a barrier that even the finest dust particles cannot penetrate. Any cables or connectors that must pass through the wall of this enclosure are specially designed to prevent dust ingress. Moving parts are the biggest challenge. The joints of a robotic arm, for example, might be covered in a flexible, multi-layered boot, like a sleeve of fabric, to protect the bearings inside. The motors that drive the wheels might be hermetically sealed, meaning they are completely isolated from the external environment. Another strategy is to simply have fewer moving parts. The design of a lunar rover is often a study in elegant simplicity, trying to achieve its goals with the minimum number of mechanisms that could be fouled by dust. We must also think about how the rover operates. The speed of the wheels might be kept very low to minimize the amount of dust that is kicked up. The process of drilling or scooping a sample might be designed to be a slow, gentle action, rather than a vigorous one. The mission might also include dedicated periods for cleaning. Perhaps the robotic arm could be used to wipe a dusty sensor with a special brush, or a puff of compressed gas could be used to clear a critical surface. The entire mission must be designed with the dust in mind, from the materials used to the way the rover moves and works. It is a quiet, constant battle against a microscopic, persistent foe. The challenge of the lunar dust serves as a final, gentle reminder of the complexity of this environment. The dangers are not just the grand, cosmic ones. They exist on every scale, from the immense, unending darkness of the crater to the microscopic, jagged edges of a single grain of dust. The dust is, in many ways, the most personal of the challenges. It is the one that gets inside, that clings and grinds and slowly wears things down. It requires a level of meticulous, patient engineering that is truly remarkable. And so, our survey of the 5 great challenges is complete. We have faced the cold, the dark, the unseen terrain, the isolating silence, and now, the clinging dust. We have seen why this is indeed the most dangerous place on the moon. Now, it is time to see how we are beginning to take the first tentative steps to explore it, not with grand leaps, but with the quiet, methodical work of our robotic vanguards. Having laid out the immense challenges of the permanently shadowed craters, it might seem as though such a place is entirely beyond our reach. But the story of exploration is a story of patience and ingenuity. We do not rush into the unknown. Instead, we send scouts, quiet explorers who map the way and teach us about the dangers before we commit to a larger journey. This chapter is about those robotic vanguards, the missions that have already begun to lift the veil of darkness and are paving the way for our first steps into the lunar shadows. Our exploration of the lunar poles did not begin with a lander or a rover, but with a listener in the sky. For over a decade, NASA's Lunar Reconnaissance Orbiter, or LRO, has been circling the moon, creating the most detailed maps we have ever had. From its vantage point in polar orbit, LRO has been patiently staring into the permanently shadowed regions. While its powerful cameras cannot see into the darkness, its other instruments can. One of its key instruments is a laser altimeter, which, as we have discussed, can map the topography of the crater floors by bouncing laser light off the surface. This is how we know the shape and depth of craters like Shackleton. Another instrument, called the Diviner Lunar Radiometer Experiment, can measure temperature. It was Diviner that first confirmed the astonishingly cold temperatures inside the PSRs, revealing them to be among the coldest places in the solar system. LRO also carries an instrument designed to detect neutrons. Cosmic rays from space are constantly striking the moon, creating a spray of neutrons from the soil. If there is hydrogen present in the soil, the key element in water, it absorbs these neutrons. By mapping the areas where fewer neutrons are escaping, we can infer the places where hydrogen, and thus potentially water ice, is most abundant. LRO has been listening to the faint whispers of data coming out of the shadows, creating the maps of light, temperature, and hydrogen that have transformed the poles from a complete mystery into a tangible, if challenging, destination. While LRO was listening from above, a different, more direct experiment was designed to get a first, fleeting glimpse inside a shadowed crater. This was the Lunar Crater Observation and Sensing Satellite Mission, or LCROSS, which reached the moon in the year 2009. The mission's plan was both brilliantly simple and dramatically effective. The LCROSS mission was launched along with LRO. After LRO entered its orbit, the spent upper stage of the rocket that carried them there was guided on a collision course with the moon. The target was a permanently shadowed crater named Cabeus, near the South Pole. The rocket stage, weighing over 2 tons and traveling at more than 5,000 miles per hour, slammed into the crater floor. The goal was not destruction but excavation. The incredible energy of the impact was designed to dig up tons of material from the frozen ground and throw it high above the crater rim, up into the sunlight where it could be seen. Following just a few minutes behind the impactor was the small LCROSS shepherding spacecraft. Its sole purpose was to fly through this plume of debris, this artificial cloud of lunar soil, and analyze its composition before making its own, the second impact on the surface. As the plume rose into the sunlight, instruments on the LCROSS spacecraft, as well as on LRO and telescopes back on Earth, were all watching. They were looking for the chemical signature of water, and they found it. The data was unambiguous. The plume contained a significant amount of water vapor and ice crystals. It was the first direct, conclusive evidence that water ice is indeed present and accessible in these dark, cold places. The LCROSS impact was a carefully planned, momentary flash of light in the darkness. It was a single, explosive question asked of the moon, and the answer that came back in the plume of debris was a resounding yes. It confirmed that the promise of the cold traps was real, and it gave the green light to begin planning for the next, more gentle phase of exploration, sending a rover to touch the ice directly. The success of LRO and LCROSS has opened the floodgates for a new generation of robotic lunar explorers. Under a program called Commercial Lunar Payload Services, or CLPS, NASA is partnering with private companies to send a steady stream of small, robotic landers to the moon. Many of these missions will be targeting the polar regions, acting as scouts to pave the way for more complex future explorations. These missions will carry a wide variety of scientific instruments. Some will be simple landers, designed to test landing technologies and study the environment from a stationary position. Others will deliver small rovers, designed to be the first wheeled vehicles to venture into the treacherous lunar night. One of the most anticipated of these missions is a rover called Viper, which stands for the Volatiles Investigating Polar Exploration Rover. Viper is specifically designed to be the first rover to enter a permanently shadowed region and map the distribution and concentration of water ice. It is a true prospector, a ground truth mission designed to turn the orbital maps of hydrogen into real-world maps of water. Viper is about the size of a golf cart and is designed to move slowly and carefully, tasting the soil with its instruments as it goes. It represents the next logical step in our patient exploration, a direct on-the-ground survey of the very resource we hope to one day use. These coming missions are the vanguard, a quiet wave of robotic scouts that will systematically reduce the risks and answer the lingering questions about the polar environment before we ever consider sending the humans into such a challenging place. The instruments that these robotic scouts will carry are a marvel of miniature engineering, a symphony of sensors, each designed to play a specific part in revealing the secrets of the crater. The Viper rover, for example, will carry a suite of 4 main instruments that work together. First, it has its own version of the neutron spectrometer that LRO carries, allowing it to detect the presence of hydrogen just below the surface from a moving platform. This allows it to see potential patches of ice underground before it even gets there. Once it identifies a promising location, it will deploy a drill. This drill, called Trident, is about 1 meter long and is designed to bore into the hard, frozen regolith. It is not just a simple drill, it also has a temperature sensor on its tip, allowing it to measure how the temperature changes with depth, another clue to the presence of ice. After the drill has created a hole, 2 other instruments get to work. One is a mass spectrometer, an instrument that can analyze the faint gases coming out of the borehole to identify what molecules are present. It can directly sniff for water, methane, or other volatiles. The other is a near-infrared spectrometer, which shines a light on the soil at the bottom of the hole and analyzes the reflected colors to determine its composition. This suite of instruments provides multiple, cross-checking ways of identifying and quantifying the water ice. They work together, from the broad survey of the neutron detector to the precise close-up analysis of the spectrometers, to build a complete picture of the resource that is hidden in the soil. It is a quiet, methodical, and deeply scientific process of discovery. And so, we see the patient, step-by-step approach that NASA and its partners are taking. We did not start by trying to land a human in the most dangerous place on the moon. We started by listening from orbit. Then, we sent a planned, carefully observed impactor to get a first confirmation. Now, we are preparing to send a fleet of robotic scouts to land on the sunlit edges and make the first, tentative forays into the darkness. Each mission is designed to answer specific questions and to reduce the unknowns for the next. These robotic explorers will be our eyes, our hands, and our chemical sensors in this extreme environment. They will teach us about the nature of the soil, the distribution of the ice, the challenges of the terrain, and the difficulties of operating in the cold and the dark. Only after we have received their reports, after we have learned the lessons they have to teach us, can we begin to responsibly plan for the next chapter. This methodical, robotic-led approach is the hallmark of modern space exploration. It is a process built on patience, respect for the challenges, and a quiet determination to understand the universe one step at a time. This naturally leads us to the ultimate question at the heart of our journey. Given all we have learned, why is a human step into this darkness still so far away? We have followed the journey of our robotic scouts as they prepare to take the first careful steps into the lunar shadows. They are our proxies, our resilient emissaries designed to withstand the crushing cold and the absolute dark. But the dream of exploration is often tied to the idea of a human footstep, a personal presence in a new world. So we must now ask the central question directly. With all our technology, why won't NASA land an astronaut directly inside one of these dark craters? The answer is a matter of profound respect for the fragility of human life. A robot is a magnificent tool, but it is fundamentally different from a human being. A robot can be designed to withstand conditions that a human cannot. We can turn a robot off to conserve energy, letting its internal temperature drop to levels that would be instantly fatal to a person. A robot does not need to breathe. It does not need to eat or drink. It does not feel fear or isolation. A human being is a fragile biological machine that has evolved to thrive in the uniquely gentle and stable environment of Earth's surface. To keep a human alive in the hostile environment of space requires a staggering amount of technology. A spacesuit is not just a piece of clothing, it is a personalized miniature spacecraft. It must provide pressurized oxygen to breathe. It must scrub the carbon dioxide from the air. It must maintain a constant, stable temperature, and it must shield the astronaut from the vacuum and radiation of space. Now imagine trying to design a spacesuit that can function in the -400-degree environment of a permanently shadowed crater. The challenge of keeping the astronaut warm would be immense. The power required for the suit's heaters would be enormous. The materials of the suit itself would be pushed to their brittle limits. Any failure, any tear in the suit or malfunction in the life support system would be catastrophic. There would be no margin for error. While a robot's mission might end with a broken wheel or a frozen joint, a human mission's failure is measured in lives. Furthermore, a robot is sent on a one-way trip with the hope of sending data back. A human must always have a return ticket. The complexity of keeping a human being alive, comfortable, and safe in the most extreme thermal environment in the solar system is an order of magnitude more difficult than keeping a machine functional. The fragility of life is the first and most important reason why we send our robotic scouts in first. A robotic mission to the crater floor is a single, complex landing. A human mission is two. Not only must you land a vehicle capable of supporting human life, but you must also land, right alongside it, the vehicle that can take them home again. This is the ascent vehicle, a rocket that must be able to launch from the lunar surface and carry the crew back into orbit to rendezvous with their command module for the trip back to Earth. The Apollo missions successfully did this 6 times, a monumental achievement. But they did it from the relatively flat, well-understood and sunlit plains of the lunar equator. Now, imagine trying to do this from the floor of Shackleton Crater. First, the entire ascent vehicle would have to survive the cryogenic temperatures for the duration of the surface mission. All of its rocket fuels, its engines, its electronics would need to be protected from the deep cold. Second, it would have to launch blind, with no human operator on the ground at mission control able to see the vehicle. The launch would have to be either fully automated or piloted by the astronauts inside, who also cannot see the surrounding terrain. What if the lander had shifted slightly upon touchdown, and the ascent vehicle was now tilted at a dangerous angle? What if an unseen rock was in the path of the engine's exhaust? The risks are immense. A launch is a violent, precisely controlled event. Attempting one from a treacherous, unseen and unmapped surface is a challenge far beyond what we are currently capable of doing safely. The burden of the return ticket is the single greatest logistical challenge of a human mission. It doubles the complexity and more than doubles the risk. Before we can even consider launching a human from such a location, we would need to have explored it exhaustively with robots, created incredibly detailed maps of the surface, and perhaps even prepared a dedicated, flattened landing and launch pad. The safe return of the crew is the highest priority, and from the floor of a polar crater, that return is simply not yet a guarantee. Beyond the immediate challenges of life support and the return journey, there are other, more subtle dangers to the human body and mind in this unique environment. We have already discussed the abrasive, clinging nature of the lunar dust. For a human in a spacesuit, this presents a significant hazard. The dust would coat the suit, and the constant movement of walking or working would grind it into the fabric, potentially wearing through the outer layers and compromising the suit's integrity. The fine dust could also get into the seals of the helmet and gloves, the weakest points of the suit. If it were to compromise those seals, the suit could lose pressure, with fatal consequences. Then there is the psychological aspect. Human beings are creatures of the light. We are fundamentally wired to operate in a world with a sun, a sky, and a horizon. Imagine working for hours or days in a place of absolute unending blackness, where your only view is the small patch of ground illuminated by the lights on your helmet. The sense of disorientation and isolation would be profound. The inability to see the wider landscape, to gauge distances, or to see your partner who might be only a few feet away would be incredibly stressful. There is also the unknown nature of the regolith itself. We believe there is water ice mixed in with the soil. When an astronaut walks, their boots will compress this soil. Could this compression release plumes of dust and ice crystals that could cling to the suit? Could the interaction of the warm spacesuit with the super-cold ground cause the regolith to behave in unexpected ways? These are questions we do not yet have answers for. We must send robots first to be our test subjects, to understand the fine details of how this environment interacts with machinery, before we can confidently predict how it would interact with a fragile human in a complex spacesuit. The unseen dangers, both physical and psychological, add another layer of caution to the prospect of a human mission into the shadows. So, if landing directly in the permanently shadowed crater is too dangerous for humans, does this mean we will abandon the idea of exploring them in person? The answer is no. It simply means we must be smarter about how we approach them. NASA's current plan for returning humans to the Moon, the Artemis program, is not targeting the dark crater floors for its landing sites. Instead, it is targeting the very places we discussed at the beginning of our journey: the sunlit crater rims, the peaks of eternal light. The plan is to land the human missions on a high, flat ridge near a crater like Shackleton. Here, the astronauts would have access to near-constant sunlight for power. They would be in a more thermally stable environment. They would have a direct line of sight to Earth for continuous communication. They could see the landscape around them, making their work safer and more efficient. This sunlit rim would become their sanctuary, their safe base of operations. From this secure location, they could then make short, carefully planned excursions into the nearby shadows. These might be short trips on a rover, or they might be done via teleoperation, with an astronaut at the sunlit base, driving a robotic rover down into the darkness in real time. This strategy gives us the best of both worlds. It places the humans in the safest possible location, while still giving them direct access to the immense scientific and resource potential of the dark craters just a short distance away. The decision not to land a human directly inside a permanently shadowed crater, therefore, is not a statement of impossibility. It is not an admission of defeat. Rather, it is an act of profound patience and wisdom. It is an acknowledgement that some places in the universe demand a different kind of respect. The story of exploration is not always about planting a flag in the most difficult spot imaginable. It is about the slow, careful, and sustainable accumulation of knowledge. We are choosing a path that prioritizes the safety of our explorers, while still allowing us to answer the crucial scientific questions. Perhaps one day, many decades from now, when we have established a permanent human presence on the Moon, when we have mapped these craters in exquisite detail with our robots, and when we have developed new technologies for life support and transportation, a human landing on the floor of Shackleton crater might become a reality. It would be the culmination of a long and patient journey. But for now, that specific journey is one for another day. The direct human exploration of the most dangerous place on the Moon is a goal that will wait patiently in the future. For the foreseeable future, we will stand on the sunlit rim, looking into the darkness with the eyes of our robotic avatars, learning its secrets from a safe and respectful distance. And in that patience, we can begin to dream of what that long-term future, built upon the foundation of this careful exploration, might one day look like. Our journey so far has been one of challenges and patient, robotic exploration. We have understood why we are drawn to the lunar poles, and why we must approach them with such caution. Now, let us allow our minds to drift forward, beyond the immediate next steps, into a possible future. Let us imagine a time when our patient exploration has borne fruit, and we have learned to live and work in this strange twilight world. This is a future written not in haste, but in the quiet, steady light of the stars. In this imagined future, the foundation of any human presence at the lunar poles would be built upon the peaks of eternal light. These sunlit crater rims, which we first identified as sanctuaries for our astronauts, would become the sites of vast solar power stations. Imagine large arrays of solar panels, not unlike those we see in deserts on Earth, but made of advanced lightweight materials. They would be spread across the high ridges, silently drinking in the constant, low-angled sunlight. Because the sun never sets here, these power plants would generate an uninterrupted flow of electricity, day after day, year after year. This is the great advantage of the poles over the equator, where any solar-powered outpost would have to endure a 2-week-long night. This steady, reliable power would be the lifeblood of a lunar settlement. It would power the habitats where astronauts live and work, the laboratories where they study the lunar ice, and the communication systems that connect them to Earth. But the power generated on the rim would not just be for the rim itself. Using laser technology, it would be possible to beam energy from the sunlit peaks down into the dark craters below. A transmitter on the rim would convert the electricity into a tightly focused beam of light, which would be aimed at a receiver on a rover or a piece of mining equipment on the crater floor. This receiver would convert the light back into electricity, powering the machine in the darkness. This concept, known as power beaming, would solve the great challenge of powering equipment inside the permanently shadowed regions without having to resort to nuclear sources for every single machine. The sunlit peaks would become the utility companies for the entire polar region, their silent, shining panels powering the quiet work happening in the frozen darkness below. Powered by the beamed energy from the rim, a new generation of robotic explorers would work on the crater floor. These would not be small scientific rovers like Viper, but larger, more robust machines designed for industrial work. They would be the ice miners of the moon. The process would be a quiet and gentle one. A large, autonomous rover, perhaps resembling a piece of construction equipment on Earth, would slowly scrape away the top layer of dry lunar soil. It would then use a heated drill or a large rotating drum to gently warm the icy regolith just enough to cause the water ice to sublimate, turning directly into a vapor. This water vapor would then be collected under a large dome or hood and channeled into a refrigerated tank, where it would refreeze into pure, clean water ice. This method, known as thermal extraction, is considered one of the most efficient ways to harvest the lunar water without having to dig up and transport tons of soil. These robotic miners would work around the clock, slowly and methodically harvesting the ancient ice. They would be supervised by geologists and engineers back at the sunlit habitat on the rim, who would monitor their progress and select the most promising locations for the next harvest. The collected water would then be transported back to the main base, perhaps by a specialized transport rover. There, it would be stored in insulated tanks, ready to be used. This vision of lunar mining is not a loud, dusty, destructive process. It is a quiet, almost surgical operation, a form of technological and environmental respect. It is a sustainable harvest, taking only what is needed and doing so with a gentle, robotic touch, all under the silent gaze of the distant, sunlit Earth in the sky. The water harvested from the dark craters would be the single most important commodity for this future lunar settlement. As we have discussed, it would provide the water, air, and food for the inhabitants. But its most transformative use would be as a fuel source. At a processing plant located at the base, the water would be split into hydrogen and oxygen through electrolysis, powered by the solar arrays on the rim. These two elements would then be cryogenically cooled until they turn into liquids, creating liquid oxygen and liquid hydrogen, the same potent rocket fuel that powered the space shuttle and many other powerful rockets. This lunar-derived propellant would be stored in large, insulated tanks at a lunar gas station. Now, the true potential of the moon is unlocked. A spacecraft destined for Mars, for example, could be assembled and fueled in Earth orbit. It would then launch from Earth orbit with just enough fuel to make the relatively short 3-day trip to the moon. Upon arriving in lunar orbit, it would be met by a tanker, a reusable space tug that has been filled with the propellant produced on the lunar surface. The Mars-bound ship would be refueled in lunar orbit, its tanks filled to the brim for the long 6-month journey ahead. This changes everything. Because the moon's gravity is only 1/6 that of Earth's, launching propellant from the lunar surface into space is vastly easier and cheaper than launching it from Earth. The lunar base becomes a critical piece of infrastructure for the exploration of the entire solar system. It transforms the moon from a mere destination into a bustling port, a gateway to the cosmos. Missions to Mars, to the asteroid belt, or to the moons of Jupiter could all begin with a refueling stop at the moon. This is the grand, long-term vision. The quiet, difficult work of extracting water from a dark, frozen crater becomes the act that opens up the solar system to a sustained human presence. The most dangerous place on the moon, once mastered, becomes the key that unlocks the door to worlds beyond. It is a profound and beautiful irony. The path to the red planet, Mars, may begin in the blackest craters of our own grey moon. What would this future human settlement look like? It would not be a sprawling city, but a compact, carefully designed habitat, likely built partially underground or covered with lunar soil to provide protection from radiation and micrometeorites. It would be a place of quiet, focused work. The habitat would be located on the sunlit rim, a place of safety and constant power. Large windows would likely face north, offering a permanent, breathtaking view of the slowly spinning Earth in the black sky. Inside, the air would be clean and fresh, recycled using systems powered by the lunar water. Greenhouses lit by powerful LEDs would grow fresh food, a splash of vibrant green in a world of grey and black. The settlement would be a mix of living quarters, laboratories, control centers for the robotic miners, and workshops for maintaining equipment. The population would be small, perhaps only a few dozen people at first, scientists, engineers, geologists, and technicians, all working together in this remote and extraordinary place. The pace of life would be dictated by the slow, steady rhythm of the work. It would be a place of immense silence, broken only by the quiet hum of machinery and the voices of the crew. There would be no wind, no weather, no changing seasons. The only clock would be the slow rotation of the distant Earth and the careful scheduling of their own tasks. It would be a city built on the edge of darkness, a testament to human ingenuity and our ability to adapt to even the most extreme of environments. It would not be a conquest of the moon, but a quiet partnership with it, using its resources in a sustainable way to create a small, glistening outpost of human consciousness in the vast, silent sea of space. This vision of a future written in starlight is a beautiful one, but it is also a distant one. It is not a future that will be achieved in a few years, or even a few decades. It is a long-term dream, and the only way to get there is through the same slow, patient, and methodical process of exploration that we are undertaking today. Every robotic scout we send, every measurement we take, every engineering challenge we solve, is a small, essential step toward this future. This grand vision is not an excuse for haste. On the contrary, it is a reason for profound patience. It reminds us that we are at the very beginning of a long journey. The future we have imagined is built upon a foundation of respect for the challenges of the cosmos. It is a dream that can only be realized by moving slowly, by learning at every step, and by understanding that the universe unfolds on its own timescale, not ours. The dream itself is a testament to the power of quiet, persistent effort, the same kind of effort that is required to finally drift off into a peaceful sleep. We have journeyed through the challenges of the lunar poles and dreamed of a possible future there. Now, as our journey begins to wind down, let us take a moment to reflect on the nature of this strange and wonderful place. Let us find the peace and the serenity in this world of extremes. There is a unique and profound beauty to be found in the unseen, a quiet lesson in the value of places that remain just beyond our easy reach. We often think of beauty in terms of presence, the presence of light, of color, of sound, of life. But the permanently shadowed craters of the moon offer a different kind of beauty, a beauty of absence. There is a serenity in the absolute, unchanging darkness, a sense of peace in a place that has been untouched by the energetic rays of the sun for billions of years. There is a quiet majesty in the profound cold, a stillness at the molecular level that is as close to perfect peace as anything in the known universe. And there is a deep comfort in the profound silence, the absence of any medium to carry sound. To imagine this place is to imagine a state of pure, elemental being. It is a landscape stripped down to its most fundamental components: rock, cold, and vacuum. In a world that is often filled with noise and constant stimulation, there is a meditative quality to contemplating a place of such perfect, undisturbed stillness. It is a beauty that does not demand our attention but rather invites our quiet contemplation. It reminds us that there is value not just in what we can see and hear, but also in the quiet, unseen spaces that lie between the stars. The permanently shadowed craters on our moon are not a cosmic anomaly. They are, in fact, likely quite common throughout the universe. Any celestial body that has a very small axial tilt and the right kind of topography could host similar regions of perpetual shadow. We see evidence of them on the planet Mercury, whose poles also contain craters that never see the sun, and where radar signals have hinted at the presence of water ice. The dwarf planet Ceres in the asteroid belt also has permanently shadowed regions. Farther out, on the moons of the gas giants, where the sun is a weak and distant star, entire worlds exist in a state of twilight and deep cold. The lunar craters are our closest and most accessible example of this type of environment. They are a local laboratory where we can study a phenomenon that is widespread throughout the cosmos. When we send our robotic probes into the darkness of Shackleton Crater, we are not just learning about the moon. We are learning about the physics of cold traps, the chemistry of ancient ices, and the challenges of exploring extreme environments that we will one day encounter on worlds much farther from home. The moon's polar craters are a gentle introduction to a universe that is filled with a wondrous diversity of worlds. They teach us that not every place is like the Earth. They expand our definition of what a landscape can be. They remind us that our own sun-drenched, water-rich planet is a rare and precious exception, not the rule. There is a deep serenity in this understanding. It fosters a sense of cosmic humility, an appreciation for the vast and varied tapestry of worlds that exist beyond our own small blue oasis. The quiet darkness of a lunar crater connects us to the quiet darkness that fills the immense spaces between the stars. We have called Shackleton Crater the most dangerous place on the moon. But what does dangerous truly mean? A place is only dangerous relative to our own abilities and our own vulnerabilities. A deep ocean trench is dangerous to a human, but it is a perfect home for the creatures that have adapted to its immense pressure. The heart of a star is dangerous to a spacecraft, but it is the engine of creation for the universe. The word dangerous, in the context of exploration, is really just another word for challenging. And a challenge is not something to be feared. It is something to be respected, studied, and eventually, with enough patience and ingenuity, overcome. The immense challenges of the polar craters are, in fact, one of their greatest gifts to us. They force us to be better. The challenge of the cold forces us to develop new materials and new ways of managing heat. The challenge of the dark forces us to create new power sources and new ways of seeing the world. The challenge of navigation forces us to build more intelligent, autonomous machines. The challenge of communication forces us to design elegant, celestial relay systems. Every problem that a place like Shackleton Crater presents is an invitation to learn and to grow. It pushes the boundaries of our technology and our understanding. The solutions we devise for these lunar challenges will have applications far beyond the moon itself. The technologies we develop for lightweight power systems, for autonomous navigation, or for mining ice in a vacuum could one day be used on Mars, in the asteroid belt, or even here on Earth in challenging environments. The value of a difficult place is not just in what we find there, but in what it makes of us in our effort to get there. It is a quiet, cosmic teacher, and its lessons are written in the language of physics and engineering. Let us listen for a moment with our imagination. What are the sounds of this new era of exploration? They are not the loud, thunderous roars of the giant Apollo-era rockets, the sounds of a race between superpowers. The sound of modern robotic exploration is much quieter. It is the gentle whir of an electric motor on a rover's wheel as it turns slowly in the lunar dust. It is the faint, rhythmic ticking of a scientific instrument taking a measurement. It is the soft, scraping sound of a drill bit boring into the ancient, frozen soil. It is the quiet hum of a computer processing data, building a map of a world it cannot see. Even the discoveries themselves arrive not with a bang, but with a whisper, a stream of binary code, a packet of data traveling silently across the void from a relay orbiter to a large radio dish on Earth. The entire process is one of quiet, methodical, and peaceful work. It is the sound of science, of curiosity in its purest form. It is a gentle, persistent hum of discovery that is slowly but surely pushing back the boundaries of darkness and ignorance, replacing them with the quiet, steady light of understanding. As we prepare to leave this place of unseen wonders, let us hold one final image in our mind. It is the image of the floor of a permanently shadowed crater. There is no wind, no sound, no light. The temperature is just a few degrees above absolute zero. The molecules in the ancient soil are almost perfectly still. It is a place of profound cosmic peace, a sanctuary of stillness that has existed in this state for longer than all of human history combined. There is a deep, meditative calm to be found in this place. It is a quiet reminder that the universe is not always a place of violent explosions and dramatic events. It is also a place of immense patient stillness. It is a place where time itself seems to slow down, where the frantic pace of our own world has no meaning. Holding this image of perfect stillness in our mind can be a powerful anchor. It is a place our thoughts can return to when we seek a moment of peace. The serenity of the unseen crater is a gift, a mental landscape of profound calm that we can visit whenever we choose. It is the perfect, quiet counterpoint to the bright, beautiful, and bustling world of our own Earth, which we will now turn to see from this unique and distant vantage point. Our journey has taken us deep into the most challenging environment on the Moon. We have explored its darkness, felt its cold, and dreamed of its future. Now, for our final act of exploration, let us change our perspective one last time. Let us imagine ourselves standing on the sunlit rim of Shackleton Crater, the safe sanctuary for future astronauts, and let us take the long view, looking not only into the darkness below, but out at the cosmos, and back towards the home we came from. Imagine standing on that high, sun-drenched ridge. The low-angled sun is perpetually circling the horizon, casting incredibly long, sharp shadows behind every rock. The ground beneath your feet is a bright, pale grey, the familiar lunar soil. On one side of you is the vast, yawning emptiness of the crater. The slope falls away steeply into a pool of perfect, featureless black. You can see the far rim of the crater, 13 miles away, also bathed in light, but the floor between is a void, a literal abyss of shadow. There is no detail, no texture, just an overwhelming sense of depth and absence. It is a humbling, awe-inspiring sight, a direct visual representation of the extremes of this polar world. You are standing on the boundary, the line between two entirely different universes. On your right is a world of light, warmth, and energy. On your left is a world of ancient cold, darkness, and stillness. To stand here is to stand on the shore of an ocean of night. This vantage point gives a profound sense of perspective. It is a place that physically demonstrates the concepts of safety and danger, of the known and the unknown. The sunlit rim is the harbour, the safe ground upon which a human presence can be built. The dark crater is the deep ocean, a place to be explored with caution and respect, using the remote tools of our robotic emissaries. From here, an astronaut could look down and see the faint tracks of a rover moving slowly across the unseen floor, its position marked only by a small dot on a digital map. They could supervise its work, sending commands and receiving its data, all from this place of relative safety. This single viewpoint, from the crater's edge, encapsulates the entire strategy of our modern approach to lunar exploration. To embrace the challenge, but to do so with wisdom, patience, and a profound respect for the line between what is possible and what is, for now, too great a risk. Now, from this same spot on the crater's rim, turn away from the darkness and look up into the sky. Because you are at the moon's south pole, the Earth does not rise and set. Instead, it hangs in a fixed position, low in the northern sky, never moving. And it is the most beautiful sight imaginable. It is a living, breathing jewel suspended in the absolute blackness of space. It is a swirl of brilliant white clouds, deep blue oceans, and the subtle greens and browns of the continents, all slowly, majestically rotating. From this distance, there are no borders, no signs of conflict, no evidence of the frantic, noisy activity of our world. There is only a single, unified and fragile-looking sphere. To see the Earth from the Moon is an experience that has profoundly affected every astronaut who has had the privilege. It is often called the overview effect. It is a sudden, intuitive understanding of the unity and interconnectedness of all life on our planet, and a deep appreciation for its preciousness. From the stark, silent and monochrome world of the Moon, the Earth appears as an oasis of color and life in the vast, empty desert of space. It is a powerful, visual reminder of what is at stake in all our endeavors. It is the home we are all connected to, the single point of origin for every human dream and every journey of exploration. To see the Earth hanging in the lunar sky, from the edge of the Moon's most dangerous place, would be a moment of profound serenity and connection. It would reinforce the purpose of the exploration to learn, to grow, and to better understand our own place in the cosmos, so that we may better appreciate the miraculous, living world that is our home. With the Earth hanging in one part of the sky, the rest of the celestial sphere is filled with the stars. And the stars, as seen from the Moon, are different from the stars we see from Earth. Here we see them through our thick, turbulent atmosphere. The air bends and distorts their light, which is what causes them to twinkle. On the airless Moon there is no twinkling. The stars are pure, sharp, unblinking points of light, set against a blackness that is deeper and more profound than any night sky on Earth. The constellations are the same, the familiar patterns of our own celestial neighborhood, but they are seen with an incredible, stark clarity. The Milky Way, the faint, cloudy band of our own galaxy, would stretch across the sky not as a subtle glow but as a brilliant, richly textured river of light, a highway of 100 billion suns. The silence of the lunar surface would be matched by the silent, steady gaze of these distant stars. This view would create a powerful sense of both time and scale. Each star is a sun, many of them larger and brighter than our own. Many of them likely have planets of their own. They are so far away that their light has taken years, centuries, or even millennia to reach you. You are seeing them not as they are now, but as they were in the distant past. To stand on the Moon and look out at the unblinking stars is to feel the immense, silent turning of the cosmos. It connects you not just to our own solar system, but to the entire, vast universe of which we are such a tiny part. It is a view that inspires wonder, humility, and a deep, quiet sense of peace. As we stand here on this imaginary crater rim, looking at the darkness below, the Earth above, and the stars beyond, we can reflect on the journey we have just taken together. It has not been a journey of physical travel, but a journey of the mind and the spirit. We began with the familiar, the comforting glow of the Moon in our own window. We then revisited the quiet triumphs of the past, the first human steps in the sea of tranquility. From there, we ventured into the unknown, to the strange twilight world of the poles, a place of eternal sunsets and endless night. We gave a name and a location to our destination, Shackleton Crater. And then we began the descent. We explored, one by one, the great challenges that make this place so difficult. The profound cold that renders materials brittle, the absolute darkness that starves our machines of power, the unseen terrain that demands a new way of seeing, the isolating silence that cuts us off from home, and the clinging, abrasive dust that seeks to grind our explorers to a halt. But we did not stop at the challenges. We also discovered the great reward that they protect. The ancient water ice, a frozen record of the past, and a vital resource for the future. We saw the patient, robotic scouts we are sending to be our vanguards, and we understood the profound, safety-driven reasons why a human step into this darkness must wait for another day. Finally, we allowed ourselves to dream of a sustainable, peaceful future, one where the Moon becomes a gateway to the solar system, a future built on patience and respect. This entire journey has been an exercise in gentle exploration. We have taken complex ideas and allowed them to unfold slowly. We have looked at a place deemed dangerous, and found in it not a reason for fear but a source of wonder, a call for ingenuity, and a lesson in cosmic humility. The true purpose of any such exploration, whether real or imagined, is not just to learn about other worlds, but to expand our own sense of what is possible, and to deepen our appreciation for our own small, precious place in the vast, silent, and beautiful universe. And so, our long view from the crater's edge comes to a close. The profound external silence of the moon is one of its most defining features. It is a silence born of the vacuum of space, a perfect quiet that has reigned for billions of years. As you lie here now, preparing for sleep, you are in your own place of quiet stillness. The noises of your day have faded away. The world outside has grown quiet. And in this moment, the silence of your room can feel connected to that great cosmic silence of the moon. It is a reminder that peace and stillness are not just found in the distant corners of the solar system. They can also be found within our own quiet moments of rest. The same silence that fills a lunar crater can also fill your mind, washing away the thoughts of the day and preparing you for a deep and restorative sleep. Let the quiet of the cosmos be your companion as you drift off, a silent, reassuring presence that connects you to the vast, peaceful universe. Our journey is now almost at its end. We have traveled to the edge of darkness and looked back at our home. In this final chapter, let us gather the threads of our exploration and reflect on the quiet, central theme that has run through our entire story: the profound and necessary virtue of patience. The universe operates on a timescale far grander than our own, and to explore it is to learn to move at its gentle, unhurried pace. The story of the ice in the lunar craters is a story written in eons. It is a tale of slow, patient accumulation. For billions of years, the cold traps have been waiting, silently collecting their cargo from the cosmos. A comet passes through the inner solar system, an event that might happen only once every few thousand years. It strikes the moon, and a few of its water molecules find their way into the darkness. The solar wind, a constant but incredibly thin stream of particles, adds its own contribution, one atom at a time. The process is unimaginably slow. We are looking for a resource that was not made overnight, but was built up over a span of time that dwarfs the entirety of human existence. It is a powerful lesson in the timescale of the universe. The things of greatest value are often the product of the longest, quietest processes. In the same way, our own exploration of this place must reflect that same patience. We cannot rush into the darkness. We cannot force the secrets of the crater to reveal themselves on our schedule. We must approach it with a patience that mirrors the process of its own creation. We send our orbiters to map the landscape for years. We design our robotic rovers to move at a crawl, to stop and study their surroundings with meticulous care. We build our knowledge base one mission at a time, one data point at a time. This is the nature of modern scientific exploration. It is not a race. It is a long, slow conversation with the universe. We ask a gentle question with one mission, we listen to the answer, and then we use that knowledge to frame our next, more refined question. It is a process that will likely span generations, a story that will continue to unfold long after we have all fallen asleep tonight. We began our journey with the idea of the most dangerous place on the moon, and now, at the end of our travels, we can revisit this idea with a new and deeper understanding. We have seen that the dangers are real: the cold, the dark, the unseen terrain, the isolation, and the abrasive dust. But we have also seen that these dangers are not malicious. They are simply the neutral, physical conditions of an environment that is very different from our own. The danger is a measure of the gap between that environment and our own current capabilities. Redefining dangerous then allows us to see this place in a new light. It is not a place to be avoided, but a place that demands our utmost respect. It is a place that tells us, come here, but come prepared. Come here, but come with your best technology, your most clever ideas, and your most profound patience. The most dangerous place is therefore also the most demanding place. And in that demand, it becomes our greatest teacher. It teaches us to be better engineers, more careful planners, and more thoughtful explorers. A place that is easy to visit teaches us very little. A place that pushes us to the very edge of our abilities is the one that forces us to grow. In this way, the danger is not a negative quality, it is an expression of the crater's unique and valuable character. It is the very thing that has preserved the ancient ice for so long. The danger is the guardian of the treasure. And so we learn to approach it not with bravado, but with a quiet, humble respect for the power of the cosmos and a deep appreciation for the challenge it presents. Perhaps the greatest lesson of the lunar poles is that the most valuable places in the universe are not always destinations to be conquered, but questions to be explored. We are drawn to Shackleton Crater, not just to collect its ice, but to answer the questions it makes us ask. How old is the water? Where did it come from? What other secrets of the early solar system are frozen there? How can we build machines that can survive such an extreme environment? The process of answering these questions is, in many ways, more important than the answers themselves. It is the process that drives innovation. It is the process that inspires a new generation of scientists and engineers. It is the process that expands our understanding of the universe. The crater is a physical embodiment of a grand scientific question mark. Its value lies not just in what it contains, but in the curiosity it sparks within us. To see the universe as a series of questions, rather than a series of destinations, is to adopt a more peaceful and sustainable mindset for exploration. It removes the sense of urgency and replaces it with a sense of enduring wonder. The questions will always be there, waiting for us. There is no deadline for discovery. This allows us to proceed at a pace that is safe, thoughtful, and responsible. The crater is not a prize to be won, but a mystery to be gently and patiently unraveled. And in that gentle unraveling we find the true, quiet joy of science. The future of our journey to the lunar poles is not a fixed itinerary with dates and deadlines. It is an unfolding path. We have a general direction, a sense of the next few steps, but the details of the path further ahead will only be revealed as we walk it. The findings of the first robotic rovers will determine the design and destination of the next ones. The challenges they encounter will inform the technologies we develop for the future. The resources they confirm will shape the architecture of a potential human base. It is an iterative, organic process of discovery. There is a great peace to be found in accepting this. We do not need to have all the answers right now. We only need to be willing to continue asking the questions and to continue taking the next careful step. The story of our return to the moon is not a single grand narrative, but a collection of many small, quiet stories of engineering, of science, and of discovery. This unfolding path extends far into the future, beyond our own lifetimes. We are simply laying the foundation, doing the careful preparatory work that will allow future generations to take the next steps, to build upon our knowledge, and to journey even farther. There is a sense of serene continuity in this, a feeling of being part of a long, unbroken chain of human curiosity that stretches from the first person who looked up at the moon and wondered, to the distant future when humans may call it a second home. And so, our long narration comes to a gentle close. We have journeyed to the most dangerous place on the moon, and we have found there not terror but wonder. We have found challenges that inspire us, and a beauty that calms us. We have found a frozen record of the past and a gentle promise for the future. And through it all, we have found a lesson in the quiet power of patience. The universe is in no hurry. The stars have been shining for billions of years, and they will continue to shine for billions more. The ice has waited in the darkness for eons, and it will continue to wait. The cosmos is always here, waiting patiently for us to explore its mysteries when we are ready. And so, you can let go of the journey now. You can release the thread of this story. There is no need to hold on to any of these thoughts. The universe will be here for you tomorrow. For now, all that is required is for you to rest, to breathe, and to allow the quiet stillness of the cosmos to guide you into a deep and peaceful sleep. Tonight we have journeyed together into a world of profound cold and unending night. We discovered that the most dangerous place on the moon is also a place of immense promise, a place that teaches us the quiet virtues of patience, respect, and ingenuity. We have stood on its sunlit rim and looked back at our own fragile, beautiful world, a small, warm haven in the vast, silent cosmos. This connection we feel to the worlds beyond our own is a gentle reminder that we are part of something magnificent. We are woven from the same stardust and governed by the same cosmic laws. You can now let this story fade, like starlight at dawn. You have permission to let go of the journey and embrace the deep, restorative peace of sleep. The cosmos will continue its silent, graceful dance while you rest. All that is left to do is to be still. I wonder, what part of our journey tonight brought you the most peace? Feel free to share your quiet reflections in the comments when you awaken. Thank you for joining me on this peaceful exploration. If you've enjoyed this time, a simple like or subscription helps others find their way to this quiet corner of the cosmos. The universe is filled with countless stories, waiting patiently to be told. When you are ready for another gentle journey, you can find our full collection waiting for you. For now, simply sleep well. Full script.